Okay, come back. Somebody say more fire, more fire, more fire, more fire, more fire. So you're back in the dance. We're gonna do some. Load on the iPad a little bit there. Chavi, load on the iPad. And your voice too. Alright, so more fire, more fire, more fire. We there, we there, we there, we there, we there, we there. Let's get this back up. If I had to do all the snaps, if I had to do all the whatever. We in for round 2. Maybe there might be a round 3 because the session going nice and smooth. Alright, but round 2 definitely trying to take us out of all the principles in chemistry. We starting back with acids, bases, and salts. Can you upload the previous live? I don't control that. YouTube controlling that. So it's take a little while to upload back. If you click on the link where you see the live, you'll still get to see it. You may not get to see from the start. You might see the last 2 hours. Right, YouTube, but YouTube is controlling that. So we're in round 2. Acids, bases, and salts. I should really and truly I should have take some time and prepare everything so that I run it a little faster. Because I'm not really a chem teacher, so I can't do it off at the top of my mind. But I should have take some time and run it through a little faster. I didn't. I took time and make a photo and post it on Instagram. And the photo was nobody wanna plan the con, everybody wanna read the band thing. Alright, so some encouragement for some people. Whatever, let's get cracking so you'll get to see me figure this out. So the topics is acid, bases, salts. Disclaimer once again, obviously I can't go from 0 to hero if you never knew nothing. Following from the syllabus, following from this book which I recommend. I can't show you contents of the book, but I'll just show you the covers. CSEC Chemistry, Anton Dale, concise. Also using this book sometimes, also using the next chemistry book that I learned some chemistry for you. So those are what I recommend. I am also functioning on 0 sleep for some while, so that's that. Okay, so let's go. How much people in the live? How much people come back? I think we had finished off with 600 last live. It's 9:40. Hopefully we can finish everything in 2.5 hours. That's it. So we'll be gunning it. We had to be gunning it. Okay, so we had about halfway, 244. So let's go. Acid, bases, and salt. What is an acid? You need to know the definitions for the acid. You see any other keywords here? 2 definitions for acids. Properties of acids and chemical reactions of acids. And basicity of acids, the acid anhydrides, and acids in living systems. I should have the syllabus open here to just run through that. So I see people putting up the definition already. You know how we do it? We just take a quick look at the syllabus. So we still have reactions, energetics to do, some other topics to rush through. We just keep moving. We just keep moving, moving along. Where did I put this acids, bases, and salts? Electric chemistry. How did I reach far down? Quite down there. That comes under number 7. So I'll just say it again. You need to define acid. I'll just say it instead of wasting time picking up the picture. You could watch your syllabus. Define an acid. Talk about acid anhydrides, base, alkalides, salts, acids, basic, amphoteric, neutral, oxide, know all of those things. Relate acidity and alkalinity to the pH scale. We'll talk about that. The strength of acids and alkalis and the basis of their completeness of ionization. Weak acids or strong acids. Weak base, strong base. What does that mean? Investigate the reactions of non-oxidizing acids. Reaction of acids with metals, carbonates, hydrogen carbonates, Talk about antacids, fire extinguishers, baking powder. Also the list example of acids in living systems. Investigate the reaction of bases with ammonium salts. Identify salt preparation, which is a big topic for some people. based on the solubility of the salt. So we'll need to touch solubility, then go into salt preparation. Can't take too long on all of these things, so I keep a nice steady pace. Dangers of salts. Distinguish between salts, acid salts, normal salts, neutralization reaction, perform calculations using the mole ratio, titration, and stuff like that. So there's a fat big chunk of principles there. Alright, so let's get cracking. The acid definition. So the first thing is acid definition. The stack one. Acid definition, and you all put it already, you could write it again. You need to know two, I think it's two. The champion one everybody's go for is proton donor, and a substance containing hydrogen which can replace directly or indirectly the metal to form a salt. So a substance containing hydrogen which replaces metal to form a salt. Keywords, right? Alright, so the general properties is the next thing you need to know. Acid properties. If you want to screenshot, you just had to make use of the double tap to just take a little go back. I think you could go back on the live bar a little bit. Acid properties, you'll need to know 4, 5. What are the properties? The properties. So what are the two definitions of acid? You remember? We just do it. The two definitions, proton donor, and then replace. Substance contains hydrogen, replace the metal to form salt. You see how the keywords is kind of linked up. So the properties, and people putting them there now. Sour taste, which is a bad property here because it's not like you're going to be tasting. Let's see if this is acid. This one is a little acid, this one is concentrated. No, you're not going to be tasting, right? So there's a bad test or anything, but it's a property. So if they say in the end of the question, what are some of the properties you can test for to show that it's acid? Don't put sour taste because nobody's going to taste it. Corrosive, blue litmus. So this is a nice one here. Red, pH value. If you use a pH meter, pH value is less than 7, and conducts electricity. So just the fact by using the word acid, you're kind of talking about in the aqueous state, right? Now to do some reactions. Acid reactions. This is how your revision go. As you make notes, think, yes, transfer from your notes textbook wherever right. Make sure you know the key points, check it back, make sure you can write it back, check back the thing we do last time, make sure you can write it back, make sure you can do a question, try a question, back, boom. The reactions. So basically 4 reactions to learn. Acid plus, I just put in A, plus a reactive metal. So you have the acid plus a base, you have the acid plus the metal carbonate, and I'm not going to put metal, I just put in M carbonate, metal carbonate. But again, I'm like a wasting paper here. I could actually write out metal. Come on, man. Metal carbonate and the acid plus metal hydrogen carbonate. So you need to know what all of these produce. Metal hydrogen carbonate. So the acid plus the metal is simple. The acid plus the metal, you're bound to get a little hydrogen gas. In fact, all of them are water except for the top one. Except for this one, if you're just doing a metal, it's hydrogen gas. Salt plus hydrogen. And all of them, you'll have a salt. So salt plus hydrogen. I'm going to put this in blue. I'm going to put the products in blue. Products in blue. And I'm going to put the products a little smaller. Salt plus hydrogen. This one is salt plus water. So the first 2 are 2, right? This one, since there's a carbonate involved, you'll get carbon dioxide as one of the gas too. So salt plus carbon dioxide plus your water, and this one is the same thing. Don't mind you see hydrogen carbonate here, we just need to balance the equation. You just need to balance the equation a little better. So next, ready for the next? You need to remember how to write your carbonate and how to write your hydrogen carbonate. Carbonate CO3, sorry for all the, this fan on my foot kind of making my thing. 8CO3, CO3 is carbonate, 8CO3 is hydrogen carbonate. So you need to know how to write your reactions. Let me get some next in the chat. So basicity of acids. What does this talk about? What is the basicity of acids? What is the definition of basicity? What is the definition of basicity? Definitions in the chat. Definitions in the chat. This talks about the number of H plus ions produced by 1 mole, right? That is basicity. How much hydrogen ions 1 mole of the acid will produce. The number of H plus ions produced per molecule. Not 1 mole, per molecule, I say mole. Alright, per molecule is a better word. 1 mole. Per molecule, yeah, because, okay, let's go for per molecule. Per molecule, like my mind can't really differentiate what happened in there right now. Per molecule of acid. Right? A squeezing acid there. So basicity is the number of H. Why people put in proton acceptor and all kind of thing. Or people now come on the live, so they're living in the past. And they refresh when they reach this part. Press refresh so you can be up to date now. You can be working with me now. The number of H plus ions per molecule of acid. So basicity talks about the number of H plus ions per molecule. So in other words, you have different styles. You have the monobasic. Give me an example of monobasic, dibasic, and tribasic. Acids. Example of monobasic, dibasic, and tribasic acids. So monobasic, yes, HCl, yes, HNO3, nitric acid, hydrochloric acid. The hydrochloric acid, for example, when you separate the hydrochloric acid, it's going, you'll have to consider a H plus and a Cl minus, you understand? Aqueous plus Cl minus aqueous. Plus the chlorine. Right? Now I have the habit of saying HCl and H plus and Cl minus. By when I'm talking and saying the letters, it kind of helps you remember instead of saying chlorine here. Right? So HCl, nitric acid, HNO3, HNO3. You can do a next here because I think everybody knows this. Dibasic, H2SO4, and this one H3PO4. Phosphoric acid. So now we can talk about acid anhydrides. What is an acid anhydride? So the acid anhydride is like before you've created the acid, before the acid was formed, there was something, there was a chemical. That the acid anhydride is that chemical. A substance that when dissolved in water, so you have the anhydride, and you add water to it, and all of a sudden, boom, acid. Some examples of acid anhydrides. Some examples of acid anhydrides. I hope my father get no sinus problem. Carbon dioxide. Why people putting definitions from what I asked 5 minutes ago? Why people living in the past? Why people don't refresh the live, press refresh, or refresh the page and press play or something? So, or press double tap to be on the verge, the cutting edge of technology. So calcium, carbon dioxide, SO3, SO2, NO2. And you should know what each one of them produce. Let's just touch on that very quickly. So like CO2 plus H2O, and this is the area I use. Reversible H2CO3. Is this balanced? Yes, it is. Let's try next one. Let's try NO2 plus H2O. This one. So the ones with carbonic acid and sulfurous acid, you have the reversible. But nitric acid or nitrous acid, you will not have. Right? Carbonic acid. Yeah, the carbonic acid. Yeah, so just pay a little attention to this. This one is a little different. So let's go straight into, so you got some nitrous and you got some HNO3. I don't know how useful this is. They might give you this formula. Good to know, right? But when you're dealing with carbon dioxide and sulfur, is a reversible reaction like this. Sulfur dioxide. Alright, so let's talk about acids in living. Why is in the chat? So you're doing preparation as well? Yes. Acids in living systems. So you need to know some examples of acids in living systems. Give me 1, 2, 3, 4, 5. 1. Somebody put stomach acid. You need to see what it does. Somebody put citric acid. You need to talk about that. Somebody put lactic acid. Metanoic acid? What the hell is metanoic acid about? Venom of ants? Okay. So you can do some research on them. I think we hit the big 3D. Metanoic acid and the vinegar. Metanoic acid. So let's just talk about this briefly. We say stomach acid. We say seeing people saying citric acid, carboxylic acid. We talk about in living organisms, eh? So subcussion acid. Stomach ACL. Okay. Right. So people have the thing down. Vitamin C. Right? C6H8O6. Vitamin C. Ascorbic acid. Must be able to talk about each one of them a little bit, like what Shanila Baker is doing. Ascorbic found in fruit has the vitamin C. So if you don't get that, you get scurvy. Sodium hydrogen carbonate is what we use to neutralize it. So if they bring it in a question, they might bring in a question and then ask you something out of that question, you understand? With balancing equations, and then you pull in moles in there and stuff like that. Citric acid, we found that in limes and lemons. Should know the reaction of rust with acid. Could be a question example, but they'll give you an idea of it. But the iron 3 plus the 6H plus from the acid reacts with the acid. The iron goes and reacts with the acid from the citric acid and leaves behind water. Ethanoic acid, aka vinegar, Vinegar used to preserve food, blah blah blah. Lactic acid when you're running and I forget what it, anaerobic respiration. You build up lactic acid, and the lactic acid is a body we have seen. Slow down, brother. The metanoic acid is in the venom of some insects. And a question, like a nice novelty question you could ask is what you could use to neutralize it. If you want to neutralize like acids from the bite, you would use sodium hydrogen carbonate, aka baking soda, or calamine lotion, which contains zinc oxide. So like to neutralize it, like acids in living system, to neutralize it, we're going to use sodium hydrogen carbonate. Sodium hydrogen carbonate. Have I 2 before that? Let me just check and make sure. Did I put the right formula for the sodium hydrogen carbonate? Yes, I did. So sodium hydrogen carbonate. This is what you use to neutralize the acids, like in living things, and they could ask you that, and they may ask you to solve the equation or something like that. Or the next one you could use is calamine lotion, and what in the calamine lotion? Zinc oxide, and zinc is in almost any kind of skin medicine. Zinc, zinc oxide. Alright, so that's enough. We get some next in chat. So then we're going to touch on bases. And I went through the syllabus so you could cover an idea of what we're doing. So about antacid. The antacid. I didn't talk about the antacid. Did I talk about the antacid? That's in the stomach. Next, we good there? Just since this man wanted to ask me about antacid, let me see if I could get on that. So next up, right, antacid, calcium carbonate. So like Aleve, is the thing you stick to? And juice, bubbles and thing. And Tums, like if you have stomach acid, heartburn or whatever, indigestion, heartburn, yeah, that's a good thing to know. So I'm glad you mentioned it. So now we know what they're talking about when they say that. Next up, bases, definition of a base. So bases, first thing you need to know is the definition. So same how acid is the proton donor, this will be the proton acceptor. I think we're good with that. Proton acceptor. Yeah. And specifically, what's the definition of an alkali? Not alkaline, eh? Definition of alkaline. Jamaican singer. What's the definition of a substance that reacts with an acid to form salt and water? That's good. That's good. Now, a base is like the chemical opposite to a salt, to an acid. And in bases, you can have metal oxides. A base includes metal oxides, metal hydroxides, and rude boy ammonia, which is not really a metal per se, but when it grouped, when those atoms come together, not ammonia, not ammonium, I want to say. If I say ammonium, it's ammonia, I want to say. And alkali is just a little different in that alkali is a base which dissolves in water to form a solution that contains, it's just a soluble base. So an alkali is a soluble base. And alkalis, alkalis will be like potassium hydroxide, sodium hydroxide, ammonia, and kinda calcium hydroxide. So the big three: potassium, sodium, and ammonia. Potassium, sodium, ammonia, and kinda calcium. Kinda. That's all we need to know. For there, so an alkali is a base that dissolves, so it's a soluble base. I wouldn't put soluble base, I'll put the definition more like a base that dissolves to form salt and water. Properties of alkalis. Alkali properties. So very quickly here on 3 properties: bitter taste, corrosive, soapy, bitter, soapy. That word is bitter, soapy, corrosive, just like metal, just like acid, but it goes from red to blue. Litmus paper, pH above 7, and electrolytes. Conduct electricity. Electrolytes. Conduct electricity. I should say conduct electricity. Reactions. Well, you know your base and your acid, salt and water, base and ammonium salt. So when heated, some bases will react with ammonium salt. So let's just look at this example. Some bases when heated react with ammonium salt. I forgot about that. So like let's say magnesium hydroxide. You're heating it, so it's a solid, plus the ammonium salt, NH4, Cl. And where is formed? What does it form? Well, I'm material sticking these days. Solid. It's gonna form salt, ammonia, and water. So what will happen is that the base will replace the ammonium, so you get salt, water, and ammonia. So that's why you just need to remember some of them. So the things like magnesium, calcium, when heated with this, there's knock out this. So you're gonna get magnesium chloride taking place now. You get the NH3 and the water, obviously, and you just had a balancer suit balancing this equation. I already put the 2 here because I was watching the book and there'll be a 2 there. 8, 6, 7, 8, right? So that's it there. So you could also look at what will happen if you have like calcium hydroxide or calcium oxide. Work. So like what will happen if I have calcium oxide? Same thing, right? Calcium oxide, and then you say ammonium sulfate, ammonium salt. So you just balance it. You just the metal is going to knock it out. Let's go forward next. Indicators of how we indicators. Again, real vex with this thing in it, not right. Indicators. Some examples of indicators, chat. All 428 of views. Give me some example of indicators. So you have the litmus, you have the methyl orange, you have the screen methyl orange, and you have your phenolphthalein. Phenolphthalein. Alright? So you have your litmus. I think that is it for y'all. Methyl orange. You have the screen methyl orange, which will change the color. Screen methyl orange. And then you have your phenol pH here. Aline. So all of them going to start off with red except the phenolphthalein, bromothiamyl blue, and yes. So all them others, and you can watch them all yourself because I'm not seeing them here, and when I was reading the syllabus I didn't really see them either. So we're just going to just quickly mention that all of these are red. This one is colorless, and these going to either blue. Well, litmus is easy, so I don't even need to write litmus. Blue. This one going to yellow. The normal methyl oranges go to yellow, and the next one is go to green. So what you need to do is just Google that and make sure you have those colors down. Yeah, the screen methyl orange go from. They're confusing me here. Let me make that second guess myself. Methyl orange color change. Red to yellow, red to orange yellow, that kind of vibes. Red to orange and to yellow, there's a phase. Yeah, screen is red to green, right? So that's what I have. So the screen is red to green, the methyl orange is red to yellow, the litmus is red to blue, and the phenolphthalein is colorless to pink. So this pink just abstract. So the people is complaining about the anomalies in chemistry. I use the anomalies to help me remember. So just because that's so out of the way, phenolphthalein, P, things started P. It's trying to think of where things to connect your brain to it. Let's talk about strength. Strength of acid, right? So let's talk about the strength of the acid. Let me take that off. Strength of acid. Spell that wrong. TH. Of acid. So you have weak acids or strong acid. What's the difference between a weak acid or a strong acid? Give some examples of weak acid, strong acid. A strong acid is one that is fully ionized in solution, so all H+ ions ionized. A weak acid is one which is partially ionized. So people did give the definitions. Now you need to talk about the same thing with alkali. Strength of acid or alkali. Let's just knock off the two things there. You just say the same thing, I guess. Say the same thing and just put alkali instead of acid. Excuse me. Give some examples of weak acids. Give some example of strong acids. Well, weak acid you only deal with the ethanoic acid, I think. Ethanoic acid. The strong acid you'll put HCl or sulfuric acid. Nitric acid. The strong alkali, you'll put any of the any of the big bosses, the big dogs, top dogs, potassium, sodium, ammonium. For the weak alkali, so for the strong alkali, you put the big boys, potassium, sodium, aluminum, maybe even calcium. For the weak ones, you'll put, my bad. Potassium, sodium, not ammonium. Did you all correct me on that? Ammonium hydroxide. I'm not too sure. Yeah, so ammonium is weak. Ammonia is the weak one. Potassium, sodium, maybe calcium. Strong one. Aluminum is an amphoteric oxide. We come into that. Alright, so you need to know your pH scale. The pH scale goes like this and like this. In the middle here, we normally designate that neutral color with green. So we have 7. And this is going to be 8, 9, 10, 11, 12, 13, 14. And this would be 1, 2, 3, 4, 5, 6, 7. Right? Or should I put that in red? Although nobody cares. 1, 2, 3, 4, 5, 6, 7. So we just mentioned that because that's easy. Stop talking, we're coming for CSEC, MS, aluminum, zinc, and lead. So let's talk about the amphoteric oxides now. You could use a pH scale to measure pH. You just plug in electrodes in it and read it off. Amphoteric oxides and hydroxides. What is an amphoteric oxide? What is the definition of an amphoteric oxide? We're going to talk about acid salt and normal salt right now after the amphoteric oxide. Whoosh. Acid salt is just a salt with a little bit of hydrogen still liming inside it, right? So I'll talk about it. Amphoteric oxide able to react with either base or acid, right? So it's a kind of weird chemical that played both sides of the fence. People paying answer for things I asked 5 minutes ago. Acids and strong alkalis, right? Because the strong alkalis are very reactive. So if you are weak, let's say you are amphoteric oxide, so you weak, you're not really there. A strong acid that quite up here, a strong alkali that quite up here, he looking down at you, and you will end up looking like you come like an acid. Then you looking kind of acidic compared to him. He will react with you too. What the hell? So, and you know your examples are aluminum, zinc, and lead. Them liming down in the middle there. Al, Zn, and lead. And you want to practice the equation for all of them. Plumates, yes. Right? Practice the equation for all of them. The amphoteric oxide or hydroxide, like zinc hydroxide. Practice the equation for all of them, the aluminates, the zincates, and the plumates. I will just do one. I'll just do the one given here, zinc hydroxide. Very quickly. Zinc hydroxide. Let's not do everybody knows zinc hydroxide reacts with hydrochloric acid area. Anyway, some time on that. NaOH plus zinc hydroxide now. So apparently Na feels more reactive. Hydroxide given here. And this is how it looks. NaZnO2 here. I would just memorize this. Plus, if I was you, I'd just memorize this like that. So I do not physics live here. I'm out, sir. I move too speedy. Yeah. Blessings if you had a rollout. Do other things in the meanwhile. You can just have the video up and you're doing your other things in the meanwhile. Do your other stuff. Don't just be waiting with me to teach you Chem right Tuesday night before Chem exam. So yeah. So that's that. So you can revise this. Make sure you know all. This is a zincate. Make sure you know all the zincate, plummet, and aluminate. It's in your textbook. It's online. Do something like that. I don't know. Waste time or to get down to things where I can explain. And finally, full classification of oxides. Classing oxides. Classing those oxides now. You have your acidic oxide, your basic oxide, your amphoteric oxide, and your neutral oxides. The neutral oxides will be like carbon monoxide, nitrogen monoxide, dinitrogen monoxide. Neutral oxides are oxides of some non-metal which do not react with acids or alkalis. Right? I didn't have that one down. So you could probably just think of that. Effervescence is the bubbles that does come from the solution. Effervescence is another word for. So them doing their own thing in the chat too. So that is, and I can do that as well. Amphoteric oxides are oxides, we don't do that. Basic oxides, we don't do that. Acidic oxides, we don't do that. We already talked about acid anhydrides, and just like that, we done that. So let's go into salts. Let's go into salt preparation now. But first, let's talk about salts. What is a salt? Definition of a salt. What is the time? Time is 10:19. We're doing good for time. We're doing real good for time. Let me just take a little stop to watch what's going on in this WhatsApp chat here. Why is you all telling me the definition of a salt and the different types of salts you have, the normal salts and your acid salts. Yeah, the salt solubility, we come into that area, and good job. Somebody, alright. So tomorrow we Anthony boys who does misbehave. Physics is next week Tuesday, or it's Tuesday or Monday. Physics is next week Tuesday or Monday. Alright, so we have the definition of a salt. A salt is something we just get from the sea. Good, you can put that get 0. A salt is a compound formed when some of all the hydrogen ions in an acid are replaced by metal and ammonium ions. Compound formed when some of all the hydrogen ions in acid are replaced. Blah 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 blah. Everybody had that. Class in salts, you either have the normal salt or you have the acid salt. The acid salts still have some hydrogen in it. Acid salts are formed when H plus ions in an acid are only partially replaced, so you only replace like one or two, like if it's phosphoric acid, you only place one, so you still end up with a. So you have the example you have is this potassium hydroxide plus. Now this will only happen really maybe what in the presence if you had limited amount of the alkali, KHSO4, H2SO4. So you notice that H there, that's what we want to get at. There's still an H there, so there's an acid salt. All the H's didn't get the boot out. Now if all the H's had get the boot out, by the way, you'll have plus water. Eh? If all the H's had get the boot out, it will not have nothing there. And we'd have just put 2 K's, and that would be that. But since that didn't happen, there's your acid salt there. Make sure you can balance the equation. I didn't balance this equation here. I didn't balance the equation, but the equation is balanced. Same amount of each atoms on both sides of the sign. Okay. Yes, only dibasic and tribasic acids can form acid salts. So every now and then I'll look at the comment section. Ignore the comments that just I'm not doing HSB. Ignore the comments that just most likely I'm not doing HSB. Ignore the comments that just trolling obviously, or the comments that cracking joke. You could watch them comments too, but you could people writing some good thing in the comments every now and then. Not every now and then, a lot of time. So there is a classification of salts there. So what they could ask them, why would an acid salt arise? It depends on how much alkali you have. It depends on how much alkali you have. The relative quantity of the reactants. So if it didn't have much moles of this now. So let's go forward. Mentioning a lot of things here. Some of the things I mentioned and I'm talking it because I'm speeding up. Any questions you could just talk about it. I'm not doing inorganic chemistry. Salts form by common acids, so we're not doing that. What's the water of crystallization? What does water of crystallization mean? Definition of water of crystallization, need to know this. And need to know the example. You need to know the example with what's called this? Copper sulfate, dehydrated copper sulfate. And what will happen if you heat it and you lost the 5 and thing? There's the amount of water in the crystal lattice. Yeah, that gives the crystal lattice its color. So definition for that, we don't really have a neat definition there. Use the word fixed proportion. So start off nice now. Yeah, Cassian fixed. There's definition there, right? Proportion, a fixed ratio. Fixed proportion of water molecules held within the crystal lattice. And it gives the crystal lattice its color. It helps gives it its color, and it helps gives it its shape. So it ain't be like dust, right? Or powder. Alright, notice formula here. Let's just go through it. You have copper sulfate, and then you put the water crystallization at that. You add that and you put it after. Now, if you apply heat, it will tell the water to get packing. You'll end up with the copper sulfate powder, and you'll end up with the 5 water separate. This is liquid. This is solid. Well, I already put it solid. This is white, so it lost its color. It's also a powder here. This is a crystal, and this is blue. So that's that. So you're gonna go through past papers. I do some past papers already, blocking the white and the thing, but that's okay. I do chemistry better at not doing past papers like this, and because a lot of it is just memorizing. So if I do a past paper, I will probably do 1% of it. If I do what I'm doing here, I will do a larger amount of work. Okay, we finally reach where we want to go. So there are lots of ways people teach this. Let's see if I remember. There's a series of questions you need to ask. You start off soluble. I'm gonna get this thing to work properly so I can draw this. Okay, let me pull up a diagram. Faster thing, boy. Preparation of salt. So I can explain this. Why? I don't like this again. Let's just to find a diagram here. I hope all you're working while I'm doing like this. I think that wasting time here. Bing, 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 ding, 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 ding. This diagram is not so sweet, but I feel I might have to use this. Let's see if I find a nicer looking diagram. Come on, guys. You all can do this. Okay, let's put this one to start off with. For each of them, I'll have to put a little something. Tell me if you're all seeing that. You all seeing that? I think you're seeing that, boy. Why is in the chat? For this, you'll need to know soluble salts and thing. Yeah, man. You seen it? I'm an internet not loading, boy. I can't believe what you're seeing now. There's some kind of bionic eyes. Let's see if I seen it. Yeah, man, I seen it too. I can't believe what you're seeing now. There's some kind of bionic eyes. Man, that's how I sung in. That's my voice, boy. Alright, so methods of preparing salts. The first thing you ask yourself, is the salt soluble? This is a little too extra, you know. This is a little too extra. Is the salt soluble? Is it potassium or sodium? Is it anhydrous? It's a little too extra. Somebody trying to send me a diagram there, but I can't really pull that from there right now. Let me see if I can find a next one. Next, I might have to actually write out this way. Anhydrous. Ding. Are we in real time looking for this diagram, boy? Time is of essence. Okay. Well, you all follow along with it. It's not like if you don't have the diagram. It's not like if you never do chemistry before. You had the diagram somewhere. I'll just shortcut it. So first thing you need to ask, is it soluble? Soluble? Are you soluble? Some other way looking away. Are you soluble? If yes, do something. If no, and the no is the lines that are going forward. If yes, do something. If no. So if no, are you potassium? Are you sodium? Are you ammonium? Are you a potassium salt? Are you a sodium salt? Are you ammonium salt? If yes, do something. The nose is the one that going down. Then finally, is it anhydrous? Wait, sir. Somebody say wait, sir. Queens couldn't burn down, man. So can you help me with integrated science? We gotta keep going. We gotta keep going. You say wait, sir, but you didn't tell them what you're waiting for. Next, everybody understand this? Anhydrous chloride. People can memorize this by themselves. This kind of important, and a lot of people was asking me to do this on and on. Why? You look tired. I am kind of tired. No. So I write no there, but you can't really see me. So I just going to disappear for a little second there. Why is disappear again? So I'm going to ask you all some questions. What do I put here? If the salt is soluble, what do I do? If the salt is soluble, what do I do? For number one, there's four main methods here. Four main methods. If the salt is soluble, no, not titration. If the salt is soluble, what do you do? Are they hearing me asking a question here, because I find I make a mistake? Oh, I make a mistake. Yeah. I'm supposed to ask insoluble. Is the salt insoluble? Yeah, thank you. That's why people are getting kind of confused. My bad. So if the salt insoluble, you use ionic precipitation. And I guess we'll have to talk about what is ionic precipitation. Insoluble, let me put that clearly. That's why the person say wait, but they know how to figure it out. If it's insoluble, use ionic precipitation. If not, is it potassium? So number 2, so people write out what number 2 is, what number 3 is, and what number 4 is. Learn it in your mind like that. Just remember this first one is if it's insoluble. And if I were you, I would write out this diagram and make sure I can write it back myself. I ain't bound to write no circle and thing. I just need to make sure I understand each thing. Number one is ionic precipitation. Alright, in ionic. Y'all, something going wrong here. Ionic precipitation. Number two is titration. Anytime it's sodium, potassium, or ammonium, we titrate. This is laboratory preparations. If it's anhydrous chloride, we just directly combine it. And you just actually take the two things and hit them together and let them do what they had to do. Direct combination. Other than that, buy-in scrap iron whole battery, Brian. So you on okay, I can repeat what you write. So do ionic bonding. Use reactive metal and insoluble base or insoluble carbonate reacting with ting. Okay, so let's look at what direct combination is. Let's look at all the preparations very quickly. Bring me back to life. Ionic precipitation. This is if it's insoluble, So if it's ionic precipitation and it's insoluble, you just need two soluble salts. You bring them together, one will replace back, and you end up with the insoluble salt prepared. So for example, the preparation, well, I guess before we do this, we need to know all the soluble salts, which big man here tell me to show you. The table of soluble salts. So make sure you know the table of soluble salts. I will just see them. I will send this just now. And I will see, I'll try to remember the method I used to just learn this, especially before an exam. Yeah man, thanks for the things. But you see how I use my iPad, and this is not an iPhone, I doesn't be able to send things from the chat to here. So those who in the chat who following. So the first thing is all nitrates are soluble. Once your sodium, potassium, or ammonium is soluble as well. And hydrogen carbonates most soluble. I don't like this one. Solubility of salts. Solubility of salts tables. Where are you? I'm a salt table solubility, right? With the exceptions. Can't remember all of them off the bat. Why? Next. The exception with bromides and all halides are soluble except the halides of silver or lead. So once you have fluorine, chlorine, you're good to go. Well, don't really deal with fluorine, it's so reactive, but chlorides now, all chlorides are soluble as well. Except like if it's silver or lead, right? Lead chloride. In fact, there's a test. That's one of the tests. So that kind of tie back in the next thing. All sulfates are soluble except barium sulfate. So you need to figure out a way to memorize the exceptions. My mind kind of shut right now, so I can give you back my way. Barium sulfate, lead sulfate, calcium sulfate, silver sulfate. Barium, lead, calcium, silver, calcium sulfate. Or calcium sulfate and silver sulfate are slightly soluble. All carbonates are soluble except all carbonates are insoluble. The carbonates is the insoluble one. Barium is partly. Yeah, partly too. So all carbonates are insoluble except sodium, potassium, and ammonium carbonate, because all sorts of sodium, potassium, and ammonium. So, show we. I'm trying to show you, I'm trying, but I'm not getting it. Some of you already have no textbook, or they sell the textbook before the exam. Okay, right, this is the best one here. this the best one? Is this the best one? Solubility of salts, so let's see in that. Just make sure and leave out anything. Silver, calcium, and carbonates, soluble, so you can snap that table. I like how that's looking. All of these soluble. Once with these is soluble. Most soluble except the silver and the lead. Sulfates most soluble. Alright. Hydrogen carbonates most soluble. Alright. So thing just know these exceptions here. Barium, lead, calcium, sulfur. Also silver. And that's about it. Can't waste no more time on this. What we are doing? Preparation. So ionic precipitation. Slowing down. Ionic precipitation. You get two soluble salts. That's basically just do the pointers. Ionic precipitation. I-precips. You want two soluble salts, and one will supply the cations, one will supply the anions. It's soluble, right? So then water soluble. Bam, when you link them up, since you're doing precipitation, the insoluble salt will precipitate. You must know your method. You dissolve, you mix, you filter, or you precipitate, and you wash it. Right? Simple. You need two soluble salts. You dissolve, you mix, wait for the precipitate to form, you filter, and you wash. And that is it. Next one, and the example is lead sulfate. Lead sulfate, or any of these insoluble salts. Any of those insoluble salts. Right? But it must have two soluble salts. People dropping out, people going to sleep. Titration method. What is titration? Titration is when you're trying to prepare the sodium, potassium, or ammonium salts. Once again, you need two solutions, one with the alkali and one with the acid. We're trying to prepare the salt here, right? Yeah, one with the alkali and one with the acid. Acid and burette. Definitions in the chat. Definition in the chat. So one with the alkaline, one with the acid. Acid in the burette. Find the volume needed to neutralize fixed amount by particular and volume of acid one fixed volume of alkali carbonate to ready water and leave to crystallize. So well, we don't really care about all of that. The alkali in your flask need your indicator. Mix the two of them until they reach a neutralization point. Leave to evaporate, and you'll get your crystals forming there. Titration, right? And the example is like any salt of potassium, sodium, or ammonium. Direct combination. This is, you just get the metal, you get the gas, keep them together, and the example for this is aluminum chloride. Right? And you just heat them together. You can write it please. Here what? Me and he doing the exam, team effort. So you got me confused. And you're supposed to be following along with your notes and your textbook too, you know. So the titration, they want me to write it. The titration was the acid and the burette. And you perform titration. With indicator. This one is the one I wanted me to bring. With indicator to either the alkali or the carbonate. Alright, inside this to try and avoid myself. Once you get the fixed amount, you do it back again. Then you redo without indicator, just so that you don't get no indicator contaminating your salt. I didn't mention that last time. So you find the fixed amount needed, you do it back, you do it back again without using the indicator. It means it did happen, but you don't have no indicator, but you already get the indicator ready. And then you evaporate, leave to crystallize, wash, whatever. You can't wash. Leave to crystallize, evaporate. You don't need to wash. If you wash, you might lose back your salt. Direct combination. Direct combination. You're going to take the two salts. So direct combination. And we're going strong. We have about 115 minutes to go again. Write out direct combination bonding. So direct combination, and you've already C and you've already R, but that's the pen writing property. In direct combination, you're going to take the metal, you're going to take the gas, bring them together via heat, and you'll get your answer. So aluminum plus chlorine, giving you aluminum chloride. Cl2, aluminum chlorine gas, solid, heat, and you balance 2, 3, 3, 2, 6, 2, right? LCM balance. Y'all keep the chat focused, please. I'm just doing some chat cleaning here. Ease me up. I'm tired, go and take a nap now. I had to keep doing this now. So all your ministry, I don't care whether it's the ministry of whatever. I had to keep it nice in the chat, right? Keep it nice and at a certain level. Have some kind of something about yourself. So you don't write in order, you'll get it wrong. Well, yeah. Why can't you do an organic chemistry? I already do all of organic chemistry. What topic is next? Next up we have redox. Redox reaction, we're going into that now. So finally, so we did ionic precipitation, titration, direct combination. You want to bring the two of them together. Make sure you do this in a fume cupboard, so you don't be breathing in all that chlorine, just so. Right? This take place in a fume cupboard. Next two or three would be using a reactive metal with an acid, or insoluble base with an acid, and an insoluble carbonate with an acid. I'll kind of leave those three are the easy three. I'll kind of leave those for you to revise. Do you want me to do them, or do you want me to go on them? Get a rate in the chat there. If you want me to do them, I'll do them. I'll go through them. Y's in the chat to go on, N's in the chat to do the last three methods of preparation. Y's to go on. N to stay. Seeing a good bit of Y's compared to N's, no. Okay, so when it's like that, I just kind of skim it. I just did titration. I just did an overview of titration, but we'll come in more to titration. We'll probably do a titration question. We're going to do a titration question. So we'll do a titration question. It looks like people want me to touch on titration. We'll do a titration question. So like if you're doing an insoluble, there are three things. You can do the metal plus acid. Right. Metal plus acid. All of them is with the acid. You can do the insoluble base with the acid. You can do the insoluble carbonate with the acid. Let's just see the differences that could happen here. This is preparation of salt. This is the last one. This is option 4. This is option 4 here. If none of these could work, you have to use that option. So you need to ask yourself those questions. If none of these could work, you have to use the option. Please do the redox. I will do redox. I will do all of them, but it'll take some time. We're going up to 12. Metal acids, metal acid, metal plus acid, metal plus acid, metal plus acid. Soluble salts will be fermenting suitable metal. You'll need the metal with the cation that you want. You'll need the acid with the anion that you want. Bring them together. Metal. This. Add the metal to the acid and warm if necessary. Keep adding until effervescence stops and the metal is present in excess. So you're taking the metal and you're putting it into the acid. Like for example, zinc and hydrogen chloride. You keep adding the zinc. Keep adding some more zinc, some strips of zinc. 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 Suppose none of this come. Well, if it didn't come, it didn't come. But if it come, this is how revision goes. You're supposed to be revising the whole thing, and it's not like we revise this little piece. That's how it goes. But that's a dark thing to think. But we do so much. We do so much for the night already. I think we started around 7 or something, 6 or 7. We do so much already. Some of it must come, right? But you keep adding zinc to your hydrochloric acid. Keep adding it. When the effervescence stop and you see zinc, some zinc in going, that means it's done. It's done. You dip some blue litmus paper inside the solution. If you see the blue litmus paper still staying blue, it means all the acid get rolled out. All the acid has been reacted. You filter to remove the excess metal. Evaporate. Your crystals remain. That is your thing. Alright? So the chat so idle. Yeah, the chat idle. I'll start to knock off some people. Y'all, if you're talking idle thing, I ain't gonna knock you off. But if you're talking like weird things or disrespectful things, I'll knock you off. Same thing with insoluble base and acid. A suitable insoluble base to produce the cation and the acid with the anion that you want. You add the base to the acid and warm if necessary. Keep adding until the base is present in excess, the insoluble base. You always need something insoluble, so you can keep adding it until you're seeing like it's not reacting anymore. Yeah, that's why the reason you start off with the insoluble carbonate, insoluble base, or the metal itself. And you keep adding it until you're seeing like it's not taking up the acid no more. You use a litmus paper just to double check and make sure you have no more acid. And then you carry through the whole process. Filter, evaporate. So in other words, all of these you add base or the metal. It's 4 steps. In excess, you use your litmus paper to check. Why is in the chat if you understand this now? You use a litmus paper to check. You're using a blue litmus paper. Blue litmus paper to check it must remain blue. Then you filter out excess. Then you evaporate the solution now, and all you'll have remain there is a salt. You must know the equations. I'll just give you some general look at the equations. For example, magnesium oxide plus like sulfuric acid, H2SO4 will give you magnesium sulfate, even though that's soluble, when you evaporate and you crystallize, you'll have a thing, plus H2O. No, if you're talking about my hairline and thing, I get thingy, you on Jones and thing. And XSS, I know you be on Jones, but like people who using rude comments and all yeah, it's no it is know when it's wrong, it's know when people overdoing it. L, right, so this is just an example. You must, so we talk about it already, base and acid, salt and hydrogen, metal and acid, salt and hydrogen, base and acid, salt and water. Enough of that. Next, let me get some next in the chat. Good day. Let's get a salts in everyday life. 383 people here. Salts in everyday life. Salts in everyday life. Examples. So you have a whole table here you can use from this book, which is very condensed. Salts in everyday life. You have the sodium hydrogen carbonate. Sodium hydrogen carbonate, aka baking soda. I was saying sodium hydrogen carbonate as baking soda from before. You have a table salt. You have a sodium benzoate. Sodium benzoate in real plenty things is a preservative. A lot of them use as preservatives. Sodium benzoate, salt, sodium nitrate, good preservatives. What is happening? The bacteria doesn't really be able to survive in that kind of pH conditions. You have a calcium carbonate from limestone, you use to make cement. Yeah, I need to get some energy. You have Epsom salt. Epsom salt. That's in medicinal purposes, calcium sulfate. So everybody already listed in the chat. What we're doing is salts, everyday life. Like I losing energy. As I lose energy, people losing energy too. People knocking out. 373 still want to sleep. Drink some coffee. I don't have coffee in my house really. I drink coffee today though. And when I was in Starbucks, I see real people from Form 6 revising pure maths. I feel sorry for them. Wear hatness, the forehead, bring like a bright like a welding machine. When my hairline come back here, it have less light to give, right? It will just have light from here to here, so we'll be good. What is a neutralization reaction? Neutralization reaction. What is a neutralization reaction, people? What is a neutralization reaction? Oh, yes. Teach, could you do balancing redox reaction? We come into that. Acid and base. A neutralization reaction is a reaction between a base and an acid to form a salt reaction. Salt and water. Okay. So we already talked about salt in everyday life. People put the explanations in the chat. Unless you are going on with me, I'm not going to write out all of that. Wasting time. Now, when you're titrating, there are some ways we can use to determine the endpoint. Or not the endpoint, the neutralization point in a neutralization reaction. What are two ways we can use to determine the neutralization point? Two methods to determine the neutralization point. Everybody know the first method. Indicator. Another method, like a novelty method, they could use temperature. Right? It will be increasing in temperature, and as soon as the temperature starts to drop back, you stop. So let me just mention this. A fixed volume of alkali is placed in an insulated container and the temperature is recorded. The acid is added in small quantities. You keep adding, recording the temperature. A graph is drawn. when the graph is drawn, you see the temperature was going up. You see two lines. You have to extrapolate your two lines because you'll keep taking readings, right? This is temperature against volume of acid. Remember, the acid is in the burette, so you keep adding acid. And you have different readings going up there. Then you'll have different readings coming down here. What you need to do is draw the line of best fit. Maybe this could come, who knows? The line of best fit. And when the two intersect, that is your neutralization point. And everybody know the indicator changes, and we mentioned the indicators already, some of the indicators you could use. The neutralization point is determined when the color change of the solution, when you just add one more drop, oops, and the whole thing change, right? So that's the neutralization point with the indicator. Any questions? Yes. So what is happening when you're adding salt and it's like isothermic reaction? The salt and the alkali, so it's heating up, and when it stop heating up, it's cooling down. When you keep adding the alkali now, when you keep adding the acid now, it starts to cool it down back to room temperature or wherever the acid was. Some examples of neutralization in everyday life. I think we talked about this. Neutralization in everyday life. Give us some examples of that, chat. That's where people mentioned the antacids. What is the formula of the antacid? Sodium hydrogen carbonate. Toothpaste. What is the next one? Soil treatment. Lime in the soil. Soil treatment. Right, so, and almost all of them is baking soda, which is sodium hydrogen carbonate. Or in the soil treatment is calcium oxide, calcium hydroxide or calcium oxide. Now, why do we lime the soil? Sometimes you don't want no acidic soil to grow whatever. Sometimes your soil sometimes your soil too acidic to grow your crop, so you put some lime on it. The lime, and then lime can be added. Lime cannot be added at the same time as ammonium. That's a good point to note. People asking me some ridiculous question. So you ever thought about starting lessons? Is that an insult? I have real lessons going on, brother. Like this year I teach so much lessons it was overloaded. That's why I'm stopping teaching. A lot of them are private because I teach one-on-one and small group lessons, like the students. The cost of that was 300 a session, 300 TT a session. So I used to go and do that with private students, and a group of them, maybe 300 TT a session each, and I'll teach that. But that's draining too much out of me. So what I do now is, what I'm doing now is trying to bring everything online. See how I'm bringing one of my maths classes online. I'm going to bring one of my maths classes online. I don't really like to teach too much chemistry, but like CAPE chemistry, but I can teach CSEC chemistry, bring that online. But before I do that, I'll bring maths. This is the order I'm going: maths, add maths, pure maths. Bring off the maths, then physics. Then I'll bring in chemistry as well. Okay, let's not waste time talking about me. You need to be able to describe all these things and the chemical that is present in all of them. These two is baking soda, and this one is calcium oxide. We talk a good bit about that. You'll hear me talking about that. Let's do the titration now before we go into the redox. Okay. So titration, aka volumetric analysis. Well, volumetric analysis is the big covering, and titration is the volumetric analysis when we're using acid, alkali, right? So this is quantitative, not qualitative. Quantitative is when you're dealing with specific numbers. Let's write a question. Now this could come all kind of ways, so you need to understand the concept more than the question itself. This question long like hell, but I have to write it out. So I'll just give me a little time to write this question here. Not that long. Before I write this, let me just see. So don't do HSB. Yeah, I don't teach HSB. Pen, I need you to work by. Not this already night. I need you to work good now by. I'm talking to you nice, right? So during titration, so some of you all can see the question too. I'll just explain it for you. Was found 15 cm cube of nitric acid and they give you the concentration 0.6 mole per dm cube. Some molar concentration. I don't need to put that slash if I put -3. It neutralized. Now they're telling you straight up here that it neutralized. They're telling you straight up here that it neutralized. Sometimes in the question you'd have to work out this. You'd have to work out how much it takes to neutralize. They'll give you the individual things. Neutralize 25 cm cube of sodium carbonate solution. They had to write it out. Sodium carbonate solution of unknown concentration. I guess maybe we had to find out that. So we have to find the concentration of the sodium carbonate, and they asking it specifically for grams per dm cube. They want the mass concentration, so they use the word mass concentration. So grams per dm cube. I double up. Excuse me. So they want the mass concentration. This is AK grams per dm cube. Right? Alright, so how are we going to find this? That handwriting though. My handwriting bad, but it's actually not this bad. Writing on this will be kind of hard. It'll be kind of hard, especially with what I have right now and all the iPad, the screening working that best right now. So, but in the future, better things coming, man. Better things coming. Alright, so okay, so let me think about the question and explain what I'm thinking in my mind too. So we got 15 cm cube of the nitric acid reacting with 25 cm cube. We don't know the concentration. So first we need to find the concentration. Okay, that's like last. Okay. So first things first, we need the little equation to see how much of this makes how much of that. We'd also need to find out this 15 cm cube here. We want to find out moles. We want to go back to moles. Remember all of the things that we talked about with grams, everything, it led to moles. Whether we have concentration, whether we have volume, whether we have mass, whether we have amount of particles, it led to moles. So we always want to kind of find back moles. So it will help this question a lot if I can figure out how many moles of nitric acid there is. Why? When I get the equation and I find out how many moles of nitric acid there is, I can figure out how many moles of sodium carbonate there is. And then if I can figure out how many moles of sodium carbonate there is, and I know the volume, I can figure out the concentration, right? So I'll find the moles, or yeah, I'll find the moles, So let me do the question as I do it. I guess that will help more. Alright, then let me see some Y's for everybody who understand how to do this kind of question. Y's if you understand fully how to do this question, and if you don't know how to do this question. We're going to do the question, but I just want to see how it's looking. So a lot of people can't see the 2 on this question. Plenty ends. Pay attention, guys. So the first manner of business, and what the good thing about it, there's kind of guide you in CXC in these questions, as I see, but they could not guide you to it if they feel incorrect. So they may tell you to write the equation. We're dealing with sodium carbonate, aqueous plus 2HNO3 aqueous. So it was sodium carbonate reacting with nitric acid. I should show you how I balance the equation and thing too. I just copy the people. I just copy NO3. So you write the equation. You may have to balance the equation. It may not give you a fully balanced equation. Aqueous liquid. Ooh, a little hungry, boy. I hear that pot moving there and a little hungry. 12 o'clock, I'm going to eat all the whole house. Alright, so that's the equation there. Why did we write the equation? We write the equation because we're trying to link the we know everything with this information about the nitric acid. We know everything about the nitric acid. So we're trying to link the nitric acid to the sodium. If you notice, to the sodium carbonate. If you notice, there's a big 1:2 ratio here. It means when I find the number of moles here, I just divide by 2 and I'll get the number of moles for this. And once I get the number of moles of sodium carbonate, I'm good to go. Yes, so we're going to find the mole ratio. Yeah, that's the terminology we use for that. That's the mole ratio. And they may ask you about that. Right? So it takes 2 moles of nitric acid to neutralize 1 mole of carbon sodium carbonate, right? Okay, so we're gonna find out how many moles of nitric acid there is now. Here's how we're gonna do that. Watch the information very carefully. You're supposed to know how to do this if you was watching the live last time. You're supposed to know how to do this if you was watching the last live. Let's do it. So what we want to find out is moles. So I put on that side, and what we're given is volume. When you have concentration, you're speaking in terms of volume, right? So we're given the volume. But this is not. Let me just go with that volume, right? You'll see what I mean. So 1000 cm cube. Hey, what really going on with you, boy? Work now, boy. If you let see me pick up this iPad and fling it across the room. Well, actually, that will be the end of the stream day. And you can say, so lose it. 1000 cm cube was the concentration, 0.6 moles. You see how this kind of technique is really help you? It's help you to think about it. So the moles is what we want, so we put on the right hand side. The volume is what we have. We're using the linker here. And we have 15 cm cube. Just a little bit. 15 cm cube will be 0.6. What's the answers? Give me some answers there, people. Over 1000 multiplied by 15 should be equal to 0.009 moles of each NO3. 0.009. Right, so you're supposed to get that. So yeah, Yay! We found the moles. So our first step was to find the moles of HNO3. The next step would be to use that information, the mole ratio, to find the moles of what we want to. We want to find the moles of what? The moles of what's the next thing? I'll have my brain just shut now. Sodium. Always was sodium carbonate, yeah. Somebody say memory banks full. That next technique guys do all the time too. I remind myself that humans are created in such a way you can never really fill up. You can become confused, you can become muddled, but you don't really fill up. It's not full. You can just keep getting more and more. You could be disorganized, it could just be going in a messy way. So what you need to do now is stop maybe and regroup, reorganize, reshuffle. Normally your brain is do this by sleeping. If you sleep now, you miss the life. Your brain is do this by sleeping. So sometimes you take a little power nap at 15 minutes to try and give your brain a little jump start into assorting back the information. Then when you wake up, you wake back up and you read over everything. Different techniques. You have to know yourself as well. So you're trying to find the moles of this. We already know the moles of HNO3. Just a little recap. The first step was to write the equation, get the mole ratio. We're going to use that. Next step was to find how much moles of this guy we have, how much moles of this guy we have. Once we found that, we was like, yay! So then now we could use that information to find how much moles of this guy. This is what we want. This is what we want. So 1 mole of this means 2 moles of that. So therefore, 0.009 moles of this would be equal to, no, it's not 1 to 2, it's 2 to 1. 2 to 1 would be equal to 0.0045. Yeah, 45 moles of Na2CO3. Why is in the chat if you understand up to here and why the logic behind this? Why is in the chat if you understand up to here and the logic behind this? Fluid or snow? No, I don't snow. Right, so again the logic behind this. One quick recap again. We write the equation, get the mole ratio, find the moles of this is the known thing. They give us a lot of information on the nitric acid, meaning you could find out about this. Use the mole ratio to find out about this now. So we breaking down some barriers here. We just found out how much moles. We just found out how much moles of Na after finding out the moles of HNO3, nitric acid. We use that information to find out the moles of the carbonate, sodium carbonate. Now all we need to do is change that moles to grams. Change that moles to grams, right? Have a little trick in here that I didn't really teach yet. Not in this part, in the next part. So what we're trying to find out now, grams of the, see how I always start up on the right hand side and put what I'm trying to find. We're trying to find the grams of the sodium carbonate, and what we have the moles right now. So using the molar mass, where the hell is the molar mass of this thing? Bam 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 bam. Ding 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 ding. Mistake, I make a mistake. People saying I make a mistake just now, eh? Moles 0.045. No, I didn't make a mistake. Well, you think I make a mistake. But I didn't make a mistake. This is for people who is like the book would do it this way, I do it the next way. I didn't make a mistake. We shall see. We shall see if I make the mistake. Yeah, you're getting marks for formula. I'm going good, I'm going good. So it's 106. I ain't going to show you how to add. You know how to do this, right? You need 2. Oh, I press. I leave out the 2. If that is the mistake you're talking about, well, whatever. But the molar mass of this is 106. So what I'm saying here is 1 mole of sodium carbonate equal 106 grams. Therefore, the 0.000 oh, there's an extra 0 here. Is there? No. I was good. So what mistake are they talking about, right? Okay, whatever. Let's keep going. We keep going. If any mistake come, it will show itself. Don't worry. If you get back lost again, don't worry. I'm going to just touch it. Just try and keep following. Try and keep following. Since this is 1, I don't need to find for 1. I just need to multiply. So it's going to be 106 grams times 0.0045. Work out that for me. Tell me how much grams we're dealing with. This is 0.4777. Right. Now, if you're watching the book, you'll see a different way, but I'm just showing you the thinking, thoughtful method. This is how much grams in how much? This represents how much grams in what? 25 cm cube. You understand what I'm saying? This is how much grams in 25 cm cube. Where the thing, right? Alright, so this is because this is how much moles there. So this is how much grams in 25. I'm gonna put a box around it. This is how much grams in the thing in for 25 cm cube of Na2CO3. Why is in the chat if you understand up to here? Quick recap again. Use the one that we know everything about. Find out how much moles in it. Use the mole ratio, find out how much moles here. Use the connection between molar mass to find out how much grams there. That's where we reach right now. We find out how much grams. And now, this is the little trick. They wanted the concentration. Concentration, you need to give it in for 1000 cm cube. You understand? You want the concentration. So since you want the concentration, I'm going to put concentration here. What do we have? This is the concentration in terms of grams, right? Concentration in terms of grams. What do we have? We have the volume here. We have something like this. Let me explain. We have 25 cm cubes being equal to 0.477 grams. This means if I want to reach up to 1000 cm cube to get the concentration, I'll need to find for 1 because this is not 1. So I'll need to divide by the 25 and multiply by the 1000, and that's going to be a final answer. You don't understand how I get the 0.045? Okay. Can the 0? No, don't round off nothing. Don't round off a single thing in this. If you round off things, you start getting wrong fast. I get an organic, but thing. So somebody want to know how I get the 0.0475. That's where the mole ratio come in handy. How I get this? Okay. Yeah, because I kind of didn't show. So if you have 2 moles giving you 1 mole. 2 moles of this, pay attention, 2 moles of the nitric acid gives, reacts, not, I keep saying gives, reacts with 1 mole of the sodium carbonate. It means if I had 8 moles of this, I'd need 4 moles of this. The ratio 8 to 4. If I had 10, I need 5. So I didn't even bother to do any calculations. I just assumed I'd catch it. If I have 9, I would need like 4.5. If it was 9, I'd need 4.5. So if I have 0.09, I just need half of that, which is 0.045. So hopefully you understand that. We're on the end here. We're on the end. What's the answer? The answer you all got? It's supposed to be 19.08. We're running out of time. 0.477. Titration is take time. .08, and that's the answer. Now when you put this answer 19.08, you need to put grams, put dm³. Alright, so I have to move on. Hopefully a good bit of people benefited from that. Don't forget to press like in the chat if you like in the video if you benefit from that. Let's go to redox. Redox reaction. This is just learning, is 11:24. Now man, we right on time. What else we have to do still? After redox, we have to do electrochemistry and energetics. Yeah, much page I turned. Alright. And how much we do before? Do all of this before. Things going good, man. Things going good. Let me hope we pass this 12 because I, man, want to do all kind of thing. Alright, so redox reaction. Sorry, CSEC other people write with pencil and they got passes. Who from Guyana? So seems boss up late helping the dudes, just multiply it equals, so it was 1 to 2. Whatever, I do the correct thing. Ethan got get big up thing, but next. Seems like no time for it. I said that you have to revise your inorganic chemistry by yourself. When we're done, I might just get some pointers. So this would mean I would have completed 80% of the first part of the syllabus, the principles. I'd have completed 99% of organic chemistry already. Maybe about 95 to be honest. So make sure you just brush up on organic chem. Don't only watch my videos, watch the textbook and thing. And I would have completed 0% of the last part, the inorganic chem, with all them qualitative analysis and thing which you'll have to do yourself. And the cycles and the impact on the living organisms and them kind of thing. You gotta do that yourself, right? There's a lot of memorizing. All your tests, disposal, identifying gases, fun stuff. Moving forward. Can the equations write with pencil? So getting me real mad by not reading my comment. Anytime somebody put that, I only get to read the vex part. I doesn't get to read the real comment. Run through green chem quick now. No, we had to go forward. We had to go forward with redox. We had to go in order. Oxidation reduction reactions in terms of electrons. What is oxidation? What is reduction? Now, the fun thing about this, I did a whole chem paper about a week ago. I did a whole chem paper. And we talk a good bit about reduction. Yes, we're going to do electrolysis and enthalpy. So the key to this is always remember in the oil rig. I find that so useful. I don't know why students just not use this. Keep in mind that the oil rig refers to electrons. Oxidation is loss of electrons. Reduction is gain of electrons. Oxidation is loss of electrons. Reduction is gain of electrons. So I'll put in the points and I'll do a question. We don't talk about that. I'll do a question. in terms of oxidation number, you should know if your oxidation number going up, like +1, +2, if your oxidation number going up, it means you're getting oxidized, right? Oxidation is the increase of the oxidation number, but the decrease is reduction. Using oxidation numbers, we had to do it in a question. In a question in cover more. Then you need to identify oxidizing and reducing agents. To me, the only thing I memorize in this, people get so much trouble with this, but ever since I was your age, the only thing I find I needed to memorize in this was this. That was it. Once I remember that, everything else stem out of that, right? You kind of need to have an idea about what oxidation number is about. But once you have your oil rig down here, people try to memorize too much thing. Memorize one thing and latch everything onto that one thing, right? So if they're talking about reducing agent now, if I'm a reducing agent, it means I'm helping you reduce. I'm helping you reduce. And if reduction is gain of electrons, it means as a reducing agent, the only way I can help you reduce is to give you electrons. Since reduction is gain of electrons. If I'm constantly gaining electrons, I'm becoming reduced. As a reducing agent, I have to be giving you electrons. And that's why I keep basing everything off of one thing instead of trying to learn everything. Right? Same thing with oxidizing agent. If I'm an oxidizing agent, I have to be taking away electrons from you. I have to be catching you to pulling away those electrons since oxidation is loss. You need to know your common oxidizing and reducing agents. Chat. Put some common oxidizing agents. Common oxidizing agents. Put some common reducing agents. But put the oxidizing agents first. If you want to see a question done on this, a past paper question, the last past paper video I think it was 2019 January. I think I do all of 2019 Jan. Correctly, the whole of 2019 Jan. You go on that video and you look for the redox question. So Fe3, look at them chat. Fe3, yeah, iron 3 plus. Iron 3 plus, the big long ones, the dichromate and the manganate, oxidizing agents, dichromate, manganate, Fe3. Sodium, the others is just hyper. Sodium chlorate, sulfuric acid, and dilute or concentrated nitric acid, them kind of thing, right? Oxidizing agents. Oxidizing anything in the reaction that taking electrons is an oxidizing agent. So if you highly electronegative, you would take electrons, so you are an oxidizing agent. If you are halogen, you would want electrons, to complete that outer shell. You are an oxidizing agent. Oxidizing agent would be like chlorine, an oxidizing agent, right? Okay. Common reducing agents will be the Fe2 plus. The Fe2 plus will want to go back up to the Fe3 plus. And potassium iodide, hydrogen sulfide gas. So those are some of the things you need to memorize. I'm not going to do any green chemistry. Hydrogen sulfide gas and HCl, concentrated hydrochloric acid. Strange one there, folks. But you need to know the color change. You need to know the color change. Color change for potassium permanganate. Generally, they give you some of these, but you need to know all. You need to know all. So here's like the first major set of memorizing. Color change for potassium manganate. This goes from purple to colorless. And the other two is orange to green. The dichromate and the Fe3. The Fe3 is the more rusty one. The Fe2 is the more green one. Yeah. So The other two is orange to green. So the dichromate, this going green, orange to green, and the Fe3 plus is brown to green, yellow brown. We'll put yellow. It's more brown. Yellow brown, yellow brown to green. That's the Fe3. Alright, so that's the that I feel like that easy to memorize. Potassium manganate, everybody's do that. Everybody know the potassium manganate crystals purple, and that will be colorless. The dichromate, green, and we also use the breathalyzer test now. So green is the thing you're looking for. Orange to green. You just need to remember the orange then. Dichromate, that green, right? Dichromate. I don't know, some other word green, right? So Fe3 plus, the higher oxidation state is the more dirtier one. So like the more yellow brown one, and it's get cleaner and it's go to green, just like the dichromate. Alright, that memorized. The other two, bro, you just look up in your table for that. Them kind of unnecessary about the brown gas and thing. That is for y'all when you're doing all the inorganic chemistry. All you can memorize them thing. Common reducing agents: potassium iodide, Ki, colorless to brown. I'd completely forget that. Colorless to brown. Why turning brown? The iodide. Yeah, the iodide being formed which turns brown. People want next, they fed up. The Fe2 would be the reverse of just now, so it'll go from green to brown, and hydrogen sulfide and yellow precipitate forms. Okay, let's go. Let's do a question. How do you test for oxidizing agent? How do you test for a reducing agent? How would you test for oxidizing agent? How would you test for a reducing agent? Just look that up online, look that up in your book, look that up in your notes, make sure you know that. Testing for oxidizing agent, use potassium iodide. Oxidizing agent causes potassium iodide to go from colorless to brown. You just use another agent to test it, right? I don't think they will bring this, but what happened? The concept of this will come inside the question. Like they will ask which one is being oxidized, which one is being reduced, which one is the oxidizing agent, which one is the reducing agent. And to me, all you need to remember is the oil rig. All you need to remember is the oil rig that deals with electrons, and you need to know what the oxidation states mean. You need to memorize the oxidizing agents, the reducing agent, the color changes, and then you can do some questions. Let's try and get some questions done. Okay, we have Fe2O3S solid. So iron oxide here. 3H2, when you have 2Fe solid plus 3H2O. Alright guys. First things first. And they're asking which reactant is the oxide. Now the reactants are these. These are the products. I'm going to do electrolysis and enthalpy. Stick with me, people. Stick with me. Let's make this finish by 12. Which one is the reducing agent? Which one is the oxidizing agent? So you get a snack. I'll find my energy dropping. If I get a snack, I will still be here. What have to eat here, boy? Yeah, eat some pineapple. That will help. I'll go for a piece of pineapple just now. Fe2O3. I'm starting to eat the tasty pineapple. I'm going to concentrate on that. Let's not go in the fridge and somebody eat all the pineapple, boy. I'm not a cursing guy, but I'm not a person to curse, but. Okay, so which one is the oxidizing? A. Which reactant is the oxidizing agent, and which reactant is the oxidizing and which reactant is the reducing agent in the following reaction? Well, let's start to watch some states now. Let's watch some states. This is 2 and 3, so this means this is 2 plus and this is 2 plus and this is 3 plus. So it means we're dealing with 3 plus here. This is 3 plus. This is now 0. Because it's a solid. Not with anything. It didn't even go to 2 plus. The rest went to 0. Fe is the oxidizing. Oxidizing is H and reducing is Fe. Fe3 plus. Well, Fe3 plus is normally just, if you look back at your table, Fe3 plus is normally just an oxidizing agent, right? Fe3 plus is just the oxidizing agent. Well, let's just verify. Okay, what shall I think of this? What shall I think of this? It went from 3 plus to 0. Which means the only way I can be positive and go down to 0 is if I'm gaining electrons. So the Fe3 plus here out here gaining electrons. If it's gaining electrons, it's taking it away from somebody. Somebody is losing electrons. Somebody is losing electrons. Going through the whole thought process here. The Fe is gaining electrons, it's being reduced, that's right. If it's being reduced, it has to be the oxidizing agent. It has to be taking away electrons from somebody. Oxidation is loss of electrons. The Fe is gaining electrons, it's taking it away from somebody, so it's an oxidizing agent. So this oxidizing agent. This O remain unchanged, right? So you don't need to talk about the O really. You can just say the Fe3 plus is the oxidizing agent. And if you figure that is the oxidizing agent, well then this had to be the reducing agent. Well, let's just verify. This went from 0 to negative . I don't know where it went to. 1? No, 0 to positive. Well, I was saying by positive 1. That's a real kill out movement there, boy. So this going up, it going in the opposite direction. I don't even need to think about anything. I don't even need to bring it down. I don't even need to bring it down to scratch. You see what happening here. You see what happening here, right? The plus 1, boop, bab, 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 bab. So we know what happening there. Let's see. So that's it. That's the question there. So that's just like a simple question. You need to be able to explain what a reducing agent is, what an oxidation agent is. Try and figure out like how I learn it. Learn the oil rig and see if you can latch everything onto that. Use that as the explanation. Oxidation is the loss of electrons. If I'm a reducing agent, I have to be helping that out. The only way I can help that out is if I gain electrons and take away your electrons. You understand? People, what the next? Let's go into electrochemistry. Made it into electrochemistry, people. This was a lot of chem, boy. How much chem is this? This is the second live. The first live went for 3 hours. This is 5 hours of chem. Electrochemistry. A crash course in chemistry by a maths teacher. Wow. Electrochemistry. You need to know electrochemical series. Some way you need to get that to fit. Write out the electrochemical series in order. I'm unable to can anymore with this. No, it will be up to them. God bless. 5 hours of punishment and studying. So write out the electrochemical series. I'm going and see if I can get a pineapple to catch something. Right. Nice. So that's the ease of ionization. Which is important to know. I'm trying to eat it too fast. Go for your own pineapple. Go in your fridge and look at pineapple. Get your own pineapple. If it's around and just watch your fridge. Drink some water and pretend it's pineapple. Somebody say easy, sir. I could have choked just now, yes. Studying while hungry is a hazard. That's a big no-no, boy. Alright, energy to go on for 4 more hours. So ease of ionization means it will displace the one underneath. So you're supposed to have your table there. It make no sense for me to write out that whole table. But like if you have a situation like zinc plus copper sulfate aqueous, is that 4? What will happen? The zinc is a wetter man than the copper now. You take away the copper. Zinc is as a sir. Copper had a relax on the outside. Hello copper. No more sulfate for you. Right? Cool. So that's easy. Just give me that. Hey, you spell strength wrong too? Ease of ionization with the non-metals. We just need to know halides and thing. Let's go on there. You need to know as a conductor versus a non-conductor. Simple. Ignore the shine on the forehead. Conductors allow an electric current to pass through. Metals, graphites, electrolytes, molten ionic compounds, aqueous solutions of electrolytes. And you need to know as a non-conductor, and examples non-conductor. Non-conductor would not allow the Samsung curve. Non-conductors will not allow electric current to pass. You need to know is electrolytes. I'm not doing them basic things. Electrolytes. Pure water is a very, very weak conductor, but just add a little bit of an electrolyte and all of a sudden it becomes a really good conductor. Just the presence of a little bit of ions just changes it. So that is why, like you see those movies where they put the electric current in the water and people get shocked, electrocuted. That is happening because it have contaminants in the water. If it was pure water, it would not really. Pure water is not a very good conductor. Strength of electrolytes. Some electrolytes are partially ionized. Give me some weak electrolytes, please. Weak electrolytes versus strong electrolytes. What are some examples of weak electrolytes versus strong electrolytes? You also need to know, I could start to draw here. Yeah, so like weak acids like ethanoate. I'm not too sure if you get titration. I'm not too sure. I think titration come in January kind of way. I'm not too sure again, question. I don't want to guess. So people give example of the weak alkali and the weak base. So they're not fully ionized, so they use this symbol. So like chuku. Something like that, right? Aqueous. What was talking about? Well, I can't remember what I was talking about, so I can move on. Oh, how like ions, I shouldn't say ions, metals conduct electricity because there are electrons in them running about the place now. But an electrolyte will conduct electricity due to the presence of ions, like sodium chloride. Now, it can't do this forever. It starts to decompose is the word. Like as the sodium and chlorine goes and move, it starts to decompose. So then it will stop. That pineapple make me feel sleepy now, but I just get a strong dish of sleepiness. I'm going to get people locking down for sleep here. So turn the page. Oh, I lost the next set. We're down to 300. We're down to the 300 people. A battery supplies the steps for the electrolysis. You need the electrolyte, you need the battery, and you need the electrodes. So let's talk about what happening here. Let me get a good diagram. So if you had problems understanding electrochemistry, this is going to help you. Electrolysis. There's some things you need to remember. Oh, nephew, I didn't know that, man. So I'm just using this diagram, first diagram I get. Okay, apparently I can use that diagram. Let's look for the second diagram I get. Din 324 people. You should know, if it wasn't told to you, the long side here is positive and the short side is negative. Long side positive, short side negative, right? So the anode is the side where the negative people go to. Anodes attract anions. Now, that's kind of confusing, right? That's confusing. The anode is positive. The anode is positive because it has to attract anions. So the fact that it's confusing is what I use to help me remember. The fact that right, so the anode would attract your chlorine, your fluorine, your whatever. It's kind of like, yeah, it had to be positive to attract the anions. And the cathode, now this have examples, chlorine and hydrogen, and we're not studying, we're just studying the basics of it so far. The cathode has to be negative. So the cathode is negative. Because it wants to attract cations. Cations are positively charged ions, and ions are negatively charged ions. What else? In the circuit, you can have a little indicator here like a light bulb to show if it's on or off, so you can know what's going on. Electrons will be moving here. The circuit will be operational. The light will be lighting so long as there continues to be sodium and chlorine in the solution, loosely in the solution, it will continue to move. But what will happen, it will discharge, it will start to discharge. The chlorine will come here. The chlorine will come here. It will lose that electron. The electron will move up this, going that way, and come down here. Understand? Electron going this way. Oh, the electron jump out. So the chlorine is negative. It goes by the positive cathode and pelts out the electron into the positive cathode and runs away. And it runs away. But when the electron goes, the chlorine will bond with the next chlorine, form chlorine gas, and bubble away. Bye. Right? That's the chlorine going there. There's a chlorine gas going there. In this solution has to be dilute for what to happen here is happening, because you're actually seeing hydrogen here. Should it? I can't remember. I'll come to that just now. I'll talk about that just now. There's conditions for brine, conditions for dilute, conditions for molten. We'll talk about that just now. And we'll also talk about inert and active anodes, inert and active electrodes. People say their head steaming. We now warming up. Think of it like we now start. Don't forget to recap. Recap. Any notes you make, recap. It's easy to recap from your notes. Alright, so the cation comes here and gains an electron, and if it's hydrogen, it will form a gas, the H2, and bubble off. Alright, let's look at a question. No. First, let's look at in molten. It's very similar. It's like that. But the problem, the thing with molten, it will only have with molten, most likely it will only have one cation and one anion, because they just melt the thing, right? But when is electrolysis with electrolytes, is normally have to try and figure out which cation coming off, which anion coming off, what happening to the electrode, all those things they have to figure out. Molten kind of easy and weird, so they wouldn't bring that. But next thing they bring that. So just take a look at the molten diagrams as well. The one they have here is electrolysis of molten lead bromide. Molten lead bromide. Obviously, the lead going to come off at the cation, and the bromine going to come off. The bromine vapor going to come off at the anion. Wow, at the anode, cathode, anode. I've seen all kind of thing. Pineapple, what are you doing, my boy? Alright, so that's about it. Red bromine vapor will show up at the anode. The lead will collect and kind of fall, because lead is heavy, it's dense, it will fall. Okay, I do moles already. You know, people, boy, when I do moles, that's the last video, I kind of confused myself too. Okay, what are the three factors that affect the discharge of the anions? What are the three factors that would affect what's happening at the anode? So if we're looking at the anode, what's affecting what happens at the anode? 1, concentration. What else? 2, 3, nature. I guess you mean the type. Type of anode. And position in series. Well, electrochemical series, yeah. Type of anode. If the anode is active, sometimes it will take part, like copper, and sometimes it can be inert, like platinum, or what's the next inert one, boy? Platinum or something else they is used to, because they won't take part in anything. Alright, so all these things affect what will come off. Now let's talk about the concentration. If you have a high concentration or something, it don't matter where it is in the series. If it just has too much, right, that going to come off. graphite. So graphite is the next inert electrode. A liquid electrode could be mercury. Good job, people. Good job. Like, this is court and tomorrow is jail. So if you have a high amount of something, and it usually applies to like brine, like when you have a brine, you have a high amount of chlorine, it don't matter what else they're coming off. So you need to compare, and this is what they bring most of the times, and I think this comes January too. Compare whether it's going to be dilute. If it dilutes and concentrate with the sodium chloride, what's going to come off. And the position in the electrochemical series, well, that's like the foundation of what's coming off. Higher it up, better the chances are you coming off. Some is 11 p.m. in Jamaica, and I realize that, and their exams start at 9, so them have a little extra time than earlier. 9 hours still drop zone. Imagine that, 9 hours and you'll be sitting in your exam, which means I'd have cut off soon, people. Very rich. Electrochemistry still have rates and energetics. Rates and energetics. We could make it. We could probably finish shortly. I'll be a lot of work done. I'll be so proud of myself. Something we do must come. Alright? So we'll have all of that, organic chemistry and anybody from Belize? 10 p.m. in Belize. So Belize like them. Belize still have 2 more hours to reach 12. Alright, so let's talk about the preferential discharge of cations. But with cations, it's a little more simple. With cations, you just want to watch the series. By the series, I mean the electrochemical series, right? You don't get too much about concentration. You also may have to look at the active or inactive. We'll see when you do a question. Okay, let's look at some examples. We're going to look at 1, 2, 3, 4, 5 examples. These are the 5 examples of electrolysis that could come tomorrow. That generally comes now, or similar to this will come. Where's the energetics? You don't know where's the energetics? That is where you're talking about the catalysts, the energy profile diagrams. So chemistry type of electrolyte. Okay, so the 5 examples we're going to look at is dilute sulfuric acid. We're going to look at dilute sodium chloride. We're going to look at concentrated sodium chloride. We're going to look at copper 2 sulfate with inerts. Then we look at copper 2 sulfate with active. So 1, 2, 3, 4, 5. If they ever bring in electrolysis tomorrow, it's some variation of this going to come. Some kind of variation of this going to come. Why is in the chat to follow with me? Why is in the chat to follow with me for the next half an hour? Stay alive, people. Remember I told you what is happening, your body is kind of go down low, as you drain and then it's get back a little energy again for some reason. That's how it's like. Y'all with me for half an hour? Belize, Guyana, Jamaica, Trinidad. Alright, so with me for half an hour. But if you have to sleep, if you are a person who needs to sleep, otherwise you'll be messed up tomorrow, go and sleep. Let me keep you up. Right? But don't go on Instagram now and waste time. Now. Some people epic with the wasting time. You know. They might finish this live and go on Instagram. Alright, so let's look at these 3 examples. The dilute H2SO4 electrolysis. Let me see if I can pull it up here instead of having to draw this, drawing is. Boom, I get here. Hey, I accident fall like that. Cancel. Boom, bam. Boom, ba bam, bang, bing. Bing, bang, bang, bang. Oh gosh, I can't use it. I can't use it. That is what you think. I will figure out a way how to use it. But so we're just going through these 5 examples. Then we'll carry on with next part, energetics, enthalpy, all those kind of things. Talk about that briefly. Why is in the chat if you see the diagram now? Why is in the chat? This is H2SO4 dilute. People messaging me and thinking about how watch your messages right now, people. So the theory diagram for the electrolysis of water acidified with dilute sulfuric acid. So it dilute, right? You have an H going by the cathode. Now, don't let this hot up your head. Normally this put the cathode on this side and the anode here. It's not so in this case. So you just think of it flipped. I can't flip the diagram. I don't know how to do that on this program. Alright, so the cathode, first you need to write out the list of everything in the solution. You have the H2O and you have H2SO4. So it means the only cations we have is H. So H must come off here. You understand that, right? You watch the cations. Some people is separated, so some teachers. I'm not a chem teacher. I would know some of the protocols that is do. So H plus. I mean, I'm not a chem teacher. Like in school, teach maths, right? So you write out this. So it has no doubt what coming off at the cathode. The H plus ion is going to come off at the cathode. What going to come off at the anode? You need to figure out which one. Which one is higher in the series. So according to this, is the sulfate ions going to come off. Oh, this one's saying sulfate, but book saying hydroxide. So maybe this is concentrated or something. Which one coming off, right? Oh no, they didn't say which one will come off preferentially. They actually put both. But if you're looking for which one will come off preferentially, the OH minus coming off, right? Here. Do that back. Somebody say do that back. First thing is a list ions. All we getting is H plus for the cations, but for the anions, we actually getting with water, you know, is write it OH minus, or the next thing is right by OH minus, or right, so yeah, OH minus. So this comes from the water, and from the sulfuric acid we get H plus and SO4 2 minus. So without a doubt we're going to get H plus coming off. This is a cation, so it will come off at the cathode, because that's what the question is be about. We're going to come off at the cathode, ting, bap, and then what will happen? And what's going to come off at the anode? Which one of these are going to come off? Preferentially, the OH minus comes off at the anode. So both of them is hydrogen, so it comes right. You understand? Everybody understand this? This is just one. This is just for H2SO4 if it's dilute. So let's look at the two settings now with NaCl. NaCl could be either dilute or it could be concentrated, aka brine, right? Now, all of these we assuming, write the ionic equations, please. Okay. Write and explain the ionic equations. So let's go back for the sulfuric acid. The ionic equation At the anode, will be the OH minus. You need 4 of it. It's normally be 4. You're missing the equations, so write the ionic equations, please. You need 4 of it. That'll be the usual. And it's always give you this 2H2O plus O2. Plus here the electrons running away, right? Is either have electrons running away or electrons coming. At the anode is positive because it's attracting anions. So the electrons is going to run up. I hope you remember that, right? OH thing, BAP. This is aqueous, liquid, gas. That is just electrons. Good there. And now the cathode. Cathode, what we see coming off of the cathode again? Oh, the cathode was just H plus ions. So you need 2 of them. And they're going to join up 2 electrons because the cathode is give things electrons. And you're going to get H2 gas now. Right? And because of that, you'll see effervescence bubbling. So, in a way, for every 4 moles of for every 4 moles of sulfuric acid, you're going to get 1 mole of oxygen. They could ask questions based on that. Remember, this was the dilute sulfuric acid. For every 4 moles of that, you're only getting 1 mole of oxygen. For every H2SO, for every 1 mole, you're getting 1. Is that 1-to-1 ratio? H2, 1, and 1, H2SO4. 1 mole of O2, every 4 mole, 1 mole of O2 and 2 moles of H2. 2, 8, 1, right, yeah. Well, for every 1 mole of sulfuric acid, mosquito got so bad. Alright, hydrogen thing, yeah. Remember I tell you, this is the mosquito room. This is not my room. I just be using this room. When we say go drink milk and sleep. We nearly done. Let me rack up this. If you had to go and sleep, go and sleep. What was I saying? OH minus taking place here. We understand this equation. I was just going into some extra thing about moles, comparing the moles, but you could just watch the equation and compare the moles. You could do that by yourself. Because of this, the result is that it will become more concentrated because you're losing water. You are losing water. So it's going to become more concentrated. Okay, somebody just touched down. Yes, so okay, that's the result. You need to know this result, right? What will happen to the solution in general? It will become more concentrated because you're removing water. So the same thing happens with dilute NaCl. With dilute NaCl, same as before for the same reasons. The H plus is going to come off because the H plus lower in the series, and the Cl is going to come off. Sorry, no, the OH is going to come off because it's lower in the series. Same as before. So you can just store that in your mind. Dilute sulfuric acid and dilute NaCl, same result. And because of that, what will happen? It will become more concentrated. Same thing, same as before. The brine is the exception, and the exception will happen where? At the anode. Because there's so much Cl, the Cl is going to come off. Even though the Cl is higher in the series than the OH minus, the Cl is going to come off. So you'll get the I'll leave out something plus the 2E minus, right? Why is in the chat? We can move on. Why is in the chat? Let's just do the last two. Let's just do the last two. Hey, we going up again or? Going up again. So how long the live going on until the syllabus completed? Nah. Hey, we're going on until our 12:30 Trinidad time. Copper 2 sulfate solution and copper sulfate solution. Now if you use inert, copper sulfate. What will happen at the cathode? What will happen at the anode? Well, you know your anode is your OH minus. Everything is OH minus by the anode, except when it's active. But everything is inert. Everything is inert, except when it's my mind in a mess. Everything is OH minus. Everything is going to be OH minus by the anode, except when it's brine and you get the Cl, or except when you have an active electrode with the copper. Cool? Good. Everything is OH minus taking place at the anode, except when it's brine, you're going to get the Cl, or except when you have an active electrode with this copper sulfate. But if you have an inert, let me say we have copper with an inert like platinum or graphite, platinum or carbon in the form of graphite, what's going to happen at the cathode is you're going to get the copper. The copper is going to come out instead of the hydrogen this time because copper just low. Copper just, I want to be out of here. Hydrogen, take your time, I'm coming out. And the copper is going to come out to the half equation for that. Remember, it's going to gain electrons, turn into copper. Sulfate, copper, just copper, solid. I really need to come off in 15 minutes. If I get kind of stumpy when we already did the equation for the OH minus. So what will happen if we have copper sulfate, but we have an active electrode, like we're using copper as electrode? Active copper electrode. The only difference, if you remember, at the anode, OH minus was taking place. So the different at the cathode, we have the same. So you learn chemistry by learning the exceptions. There's a tip in learning chemistry. But at the anode, you have the copper doing the reverse. The copper is turning around and do the reverse. Instead of OH minus, the copper turning it around and doing the reverse. So you end up with copper 2 plus 2E minus, giving you back copper solid. So you're losing copper on this one and you're gaining copper on that one. Thank you, sir, for helping us. People falling like flies. We had to go just now. It was real nice. I will just briefly touch energetics. That'll be the last thing. Rates of reaction and energetics. I'll just briefly run through that in probably like about 15 minutes and we'll be done. Alright. So you could revise that by yourself as well. Go it over. Remember to recap. In the morning you want to recap everything out of your notes. You may not want to learn anything new, you want to try. Oh shucks, I put this wrong. It should be minus. Because no, this should be plus. Is this minus or plus? This is plus. This is correct. This is plus. Don't do it. Yeah, why in the chat if Syllabus we get in synthetic? The man say why in the chat if Syllabus, and the rest put some more, and they better put some more in them in the chat. I now reach and he going, well, look trouble. You now reach? How people is now reach? Boy, what's really be going on, boy? Alright, so that's electrolysis for you there. There's a part in electrolysis we left out, the part with the Faraday, where you need to link Faraday. I don't want to leave it out. I really don't want to leave it out. Next time it come, I'm feeling bummy. the Faraday constant. This is the constant that links everything. Right? That's the Faraday constant. What do you know about the Faraday constant? Tell me the definition for the Faraday constant. Tell me the definition for this Faraday's thing. So people don't know about the Faraday. They don't know about the Faraday, boy. I know nothing. So you need to know this, and you need to know Q is equal to IT, and you need to know that definition for the Faraday constant. It basically is this. This is the amount of current in 1 mole of electron. That's it. Faraday's constant, 96,500 coulombs. 1 mole of electron contains 96500, right? Coulombs. That's it. 1 mole of electrons contain that amount. Now, how we'll use that in a question, let's just briefly do a question on it. If this question come, I'll be so happy because I didn't leave it out and it come. So, calculate the volume of oxygen produced at anode. We delimit RTP here, and the current is 5 amps. They will walk you through this question. If they bring it in question 1, they'll walk you through it. 5 amps pass through dilute, and you're using NaCl dilute, aqueous, right? Dilute. And they give you a time, 3 hours. A real specific time, 3 hours 51 minutes 36 seconds. Right, so how would you do a question like that? You want the volume, look at the handwriting. You want the volume of the oxygen at the anode. They give you how much current, and they give you the time. Well, the first thing to do is get a Q. Get a Q. Get a Q all the way. Q is equal to IT. Right? So Q is equal to IT. So the I is 5. The time must be in seconds. So this, you need to change this to seconds. So changing 3 hours to second, you'll need to multiply this by 3600, or 60 by 60. So the 3 hours, so this will be 3 by 3600 plus, I just change the hours to seconds, plus I need to change the minutes to seconds, so just multiply by 60, plus I need to add that extra second there. It was 36 seconds. And the answer for this is how much? How much coulombs are they get for this? This has to be in coulombs. I didn't see no answers. Give me some answers. Five multiplied by this. Yeah, we're going to the energy profile diagrams just now, but this could come. Watch this. Energy profile diagrams, I have a strong feeling that we're going to come to, so I'm going to do that. Somebody want me to do this over? I didn't do nothing yet. I just finding Q is equal to IT. I finding the coulombs, and I'll tell you why I finding the coulombs just now. So remember, I is the current, which is 5, and T is the time, which I worked out here. Right. So somebody give me the answer there. 69480 coulombs. Once I find the coulombs, I need to attach this. Find the volume of oxygen produced, 1 mole of electrons, ding ding ding, 1 mole of electrons are lost in forming 1 mole of oxygen. Alright, so I need my half equation. With this you're using the, hey, this mosquito don't wanna die, boy. With this you're gonna use the half equation here. You're gonna use the half equation. Remember, the half equation is OH negative at the anode now. giving you 2H2O plus O2. This is the OH equation. You just need to memorize this equation for E. G aqueous. So what we see in here, boy, this had to be 4. What we see in here? The thing we need to watch really is here, because the coulombs talks about the coulombs here talks about the electricity. So we're not watching this like if we're doing moles, we're watching the electrons. So this in balance. Oh, 1, 2, 3, 4, 1, 2, 8 balance. Right, so this is 4 moles giving you 1 mole. Right, so 4 moles E give you 1 mole O2. How many moles did we have? Well, we could find that out because we have a connector. Where's the connector? This. Oh, sorry for the energy being a little low. Sorry for the energy being a little low, people. Sorry about that. This is the connector. So 69500, which is basically this, is equal to 1 mole. So therefore this amount 694,800 will be, let me say 1 mole, right? Let me say 1 mole. So we have 1 mole. We actually had 1 mole taking place there. So if you don't understand this, I'm not doing it over. Sorry, you had to watch it in the textbook, you had to watch it over. I'm not doing it over. If you don't understand it, sorry. I'm not doing it over because I need to do the energetics diagram before time runs out. So we had 1 mole taking place here. So it means we can assume, since 4 moles will give us 1 mole, just now, 4 moles of electrons versus that. 4 times that is that. They do a real unnecessary calculation in this thing, boy. Oh god. Yeah, they make this a little more difficult than it is. So let me just use my explanation technique. Calculate the volume of O2 produced. The anode current thing, blah blah blah. We found the amount of coulombs. So that means we practically gain 1 mole there. The second one 0.1. 4 moles of electrons will produce 1 mole of oxygen. We only had 1 mole of, we only had 1 mole. We only had 1 mole. So we had 1 mole of electrons. So this means we had 1/4 moles of O2, which means we had a quarter. We had a quarter of that. Why are they getting a different value? What am I doing wrong? Almost. I lost in the forming. Four moles of that form that. 4 times that forms that. Thing forms that. Let me just try it one more time. If I don't get it this time, I'll have to go on because I just not in a state to get it. 4 moles of electron give me 1 mole of oxygen. 1 mole of electrons is 965. So this is 4 by 96500. So that's wrong about the book, giving you 1 mole of O2. This is coulombs. So we have 3, work out that for me. 4 times 96500. We have 38600 coulombs, giving you 1 mole of O2. Right? So that's why you had to take this question. Sorry about that. And then how much we had? 96480, I think was the number. Would give you 1 over 386,000 multiplied by 96480. So this will be equal to how many moles of O2 present? I've gone below the line there. We got a number for me, so don't hot up your head. Now hotting up my head. Somebody understood this just now, and it might help them. So this, even if it will help them now, it might help them any levels. So this is 0.18 moles of O2, right? 0.18. Now once you have the moles of O2, you're practically done. Because they'll say 1 mole at RTP is 24 dm cube. 0.18 moles would be 24 times 0.18, which would be 4.32 dm cube taking place. Quick recap before I go on. Use this formula, find out how much coulombs you're dealing with. Use the half formula, find out the mole ratio, but you're using electrons to whatever it is you want. Whatever it is you want. Say, do it like this, not like how I was trying to do just now, but I feel like how I could do just now could work here, but I make a mistake. Say it wrong. Say that wrong. It's wrong though. Why people saying it wrong? Say it wrong. So is 6 9. It's not that amount. It correct. No, I correct. I want to go to what this so. Check over your word. No, it correct, it correct. It correct, people. I verified with the book and I'm pretty sure it correct. It can't be a big number like that. You know how much dm cubes is that? 69480 dm cubes. It can't be a big number like that. If that big number, I mean, wow, you just take a little small experiment like this and you fill up a stadium full of air with hydrogen. It's not that. It's not that. It's not that. So let me just recap it again for the people who are saying it wrong are correct. You start the equation, you work out how much coulombs we have, and how much coulombs was given to this electrolysis. Use your half equation to find the relation between the. It will almost always be this if they're using oxygen, if they're using the anode, because I told you what are the conditions. And if you get a ratio 4:1, you set up your ratio, you multiply, because every 1 stands for 9650. You get how much coulombs you need to produce it. Then you use how much you get, you find for 1 then, and then you find for how much coulombs you have. That will give you the moles. Once you have the moles, well, we do this already. Once you have the moles, 1 mole is this amount, so 0.8 moles is that amount. So good. Straightforward, straightforward. Hopefully somebody caught that there. I see people saying say you're correct. Next. Alright, so the next step is, so you all will have to also check up electroplating and extraction of metals from their ores and something called anodizing. That is on earlier. Trusting earlier with that. Don't let me down. Alright, so let's go into rates of reaction, energetics. What is the rate of a reaction? What is the rate of a reaction? 10 more minutes, 10 more minutes. It correct. What I do correct. Forget bother. Forget bother if you think. Forget bother. Some of them people trolling. Them trolling. Define the rate of reaction. Waiting on the rate of the reaction. Mr. Jamaican Bacon. Is Mr. Jamaican Bacon giving trouble? What he say? Why you times it by that? You have 6. No, I don't. But he don't understand. No, not cubed. You use the wrong value. Why him not check him chat? Say that wrong. No, it's correct. Jamaican, you can message me on Instagram. So either they're trolling or just whatever, yes, either they're trolling or thing. Check my Instagram. I need to know whether they're trolling or they're for real or they're for real. Whatever. Let's move on. So rate of reaction, this could come. Remember the rate of reaction, people put the definition. Is either the decrease in the concentration of the reactant or the increase in the concentration of the product. So the decrease in concentration of reactant and the time taken for the step. I use 96480 when it's supposed to be. Oh no, this one. Oh, okay. I just make a okay. They're correct. They're not trolling. I just make a mistake here. Somebody told me that, but apparently it's 96. And I keep saying 9. Either I make a mistake when I was writing it. Or some. Let me check it. I don't rely on nobody. Let me check it for myself. 5 times. Did I check this for myself? It wasn't trolling. 3 times 3600 plus 51 times 61. I hate to make convoluted mistakes. Plus 36. That's why they say it wrong. It wasn't trolling. Sorry fellas for thinking I was trolling. So I am getting what I had here. So we're back to trolling now. I am getting what I had here. 16. Pop. 69. I was rushing through. 69. And that's how they get this. This answer was taken from the textbook, as I said. Is that the part? Are we on the same page now? Everybody happy now? Why is in the chat if everybody on the same page? I hope is that. Alright, wait. So 69 there. So this answer, I didn't use my calculator for this answer. I just take this answer. So hopefully this answer correct. This answer taken straight from the example. So apparently I pulled this from my mind when I was writing. I remember that. I just pulled this from my mind and I mix up the 6 and the 9 and I just take the answer here. So that was small thing. That's small thing, man. Small thing. Alright. So rate is that. So we're moving forward. Thanks fellas. What are some techniques used to measure the rate of reaction? What are some techniques used to measure the rate of reaction? You also need to know is the collision theory. You need to know to draw your rates of the curve. You all know this? You all know rates? You all know rates, so we can move on. You know the theory. I've seen plenty of people saying next. So I'll just talk about it then, see, since everybody know it. The rates of the reaction, right? So we use the volume of the gas, whether it's decreasing in mass, a change in the color, pressure, temperature, or pH. Color, yeah, pH. Color intensity, pressure, temperature, or pH. Color intensity, vague to measure. Or the appearance of a precipitate. All of these things we use to measure the rate of a reaction to see how far along it's going. What is the collision theory? Once you'll explain that, I'll be looking at the other things. What is the collision theory? Also, what are the factors that affect the rate of reaction? You need to know what doesn't affect the rate of reaction and what affects the rate of reaction. What is the collision theory? Nobody put that up yet. Your general rate diagram. You know, your general rate diagram would look like this. This is the reactants. The reactants getting heat up. And this is your product. You start off with no product. But then, right? So, nobody put the collision theory up, boy. Nobody write the collision theory yet, boy. It's so long. There are three things in this states that the ions should collide facing each other in order for reaction to take place. During any chemical reaction, the existing bonds in a reactants must break so that the new bonds can form in order to react. Three things need to happen: sufficient speed, correct orientation, what else? Sufficient speed or sufficient energy, kinetic energy, sufficient energy, the correct orientation, and they must collide, right? So whoa, all of a sudden everything gets poured out. Good. So that is a collision theory. Must collide, and I like to remember things if they are in threes. Helps me. Must collide. They must be properly orientated. Remember the correct words. And they must hit with the right amount of energy, right? Enough energy to the minimum amount of energy needed is called the activation energy. Alright. Any collision that results in a reaction is known as an effective collision. And that's about it. We good there? Why is in the chat? I just want to say sorry again to the people who asked. Well, I didn't really see how that's true. Now, the kind of person I am that's come in handy. As lawyer sometimes for those, I get that from, and then you saw always be so. I get that from my wife. Don't come down on people immediately and never know what side they're coming on. Sometimes you could be wrong. So I thought in my mind maybe they are trolling, but I was wrong. I had read the wrong thing on one part of the question. So sorry about that, Mr. Jamaican Bacon. Love and respect. Lengthy physics Saturday and Sunday. Definitely I'm going to be down in physics. Physics is my thing. Chemistry is not really my thing. I'm using textbook, I'm using syllabus and things for chemistry. For physics, I could teach that more from my mind and ramble more about it and be very sure about certain things. Alright, so the rate curve. Here we have our products. Here we have our reactants. We're doing enthalpy next. So that's about it. You need to be able to describe what is going on here. At the beginning, the slope is high, right? The slope is high on both of them because they're being used up faster. But as it starts to go on, is like in the earlys when a young lady in her 20s from 18 to 30, pristine, best. This is society. I don't come down and man hit me with no feminist thing. I just saying how the world is. Everybody wants to be with her. Prime target for marriage. But as the biological clock begins to tick and she crosses 30, 35, 40, It just has less choices now, boy. It just have less choices. So it's the same thing when reaction as move on. Some people can't wait for the live stream to finish. So as the reactants going along, it just have less reactants to make products. It just have less, so it kind of fizzles out. You must collide with it at the right orientation. Oh my gosh, somebody not answering that question from so long ago. So just a quick read of this. At the beginning of the reaction, the gradient is at the steepest, showing the rate at its highest. The concentration of the reactant particles is at its highest because the frequency of collisions is very high. Frequency of collision is a word, that term you want to use. It decreases and it eventually becomes horizontal, meaning it doesn't change again, because at this point either one of the reactants has been used up and there's no nothing left to collide. Yeah, one of the reactants has been used up, so there's nothing left to collide. You get used up, right? So like when you remember when you was doing putting the zinc into the acid, you just keep putting the zinc, and after a while you just start to see zinc getting left behind because you use up all the acid, man. What are the factors that affect the rate of reaction? What are the factors that affect the rate of reaction, people? Surface area, concentration, temperature, presence or absence of a catalyst. That will affect the rate. Pressure can affect the rate of the reaction too in gaseous states. Right, and you need to state why. Concentration, more to react, temperature, higher energy, all of them either affecting one part of the collision theory. Surface area, if you have to make it finer, if you, like for example, I used to do this thing when I was younger. I used to take flour from my mother, flour bowl or whatever, and just throw it over the fire. So I used to make a big kind of explosion looking thing, and she used to get mad, but powder is actually extremely flammable because the flour is actually extremely flammable because it's so small, right? So if you make things smaller, it will dissolve better. That's why you break up stuff when you're trying to dissolve it. Okay, enough talk about that. You must know why each one of them affects the rate of the reaction. Why would the concentration affect? The graph of it. So for concentration, if you increase the concentration, you see generally something like that taking place. If you increase the temperature though, you see something like this taking place, right? The rate of reaction go up like this, right? Anything I left out here? Any questions? I think I talked about everything here. They talk about why the flour mills and the coal mines, it could be explosive with the small particles. Same thing I'm telling you about. Alright, so we good with that. 256 people. Effect of change in rate curves. Increasing the thing. Well, in CAPE you go into that in more detail. Remember, you can increase the rate of the reaction, you can decrease the rate of the reaction, but at the end of the day, you're still going to get the same amount of product. So that could be a question, especially in your multiple choice. Energetics, we are the last. What's the equation we need to know for energetics? E is equal to MC delta theta. We are the last. We are supposed to finish 12, we might finish minutes to 1. E is equal to H is equal to MC delta theta. That's the formula you need to know, right? So I guess I'll just do one question, explain the graphs. You know your graphs are exothermic and endothermic look like this. Reactants, if this is the energy they contain, if the reactants start off here but they end up here, it means they lost the energy. You understand? They call this the delta H. The delta H is negative, and if they're losing energy, this is exothermic. If the reactants started off here and then end up here for the products, and is actually for reactants and products here. This is the reactants and products. If it went up, meaning the reactants, between the reactants and the products, energy was gained, this delta theta, I say delta theta, delta H, okay, is positive. That means energy was gained from the environment, so it's a endothermic reaction. Endothermic reactions make the place colder, exothermic reaction make the place hotter. But it kind of in reverse when you watch the energy, right? It come down, the energy fall down because energy given out to the environment. Now it doesn't really look like that. It will look more like, if you want to draw the energy profile diagram properly, it will look more like this, a little bump and a drop. What is this little bump about? Class, what is this little bump about? 265 people, what is this bump about? This one is the exo. Delta H, keep in mind the delta H is still from this part. Yes, so somebody said it, this is the activation energy. This is the amount of energy is had to put in to start the equation. Equation. I need to sleep. The amount of energy you put in to start the reaction. Activation energy is the minimum amount of energy that reactants must be given in excess of what they normally possess, so that the bonds start breaking and the reactants and products start forming, right? Make sure you know how to define your activation energy. Now you should know how to do a little question. Let's do one question involving specific heat capacity, and I will go and sleep. There are three things to determine. Oh, just two things now. Heat of solution, heat of neutralization. Heat of solution, heat of neutralization. What is the definition for it? Please do heat of neutralization. Okay, I'll start off with heat of neutralization. What is the definition for heat of neutralization? Endothermic does not make mecha. Endothermic doesn't make the reaction vessel warmer, it makes it colder. It takes in heat from the environment. Exothermic will release, so exothermic will make it warmer, endothermic will make it colder, right? What is the definition for heat of neutralization? Somebody just write that there. Heat of neutralization, the amount of energy produced per mole of water in the reaction. No, that's not good. Energy change that occurs when 1 mole of water is produced. Right. So when 1 mole of water is produced, the amount of energy you get from that. This question long like the road, boy. So let me just do this question then. A heat of neutralization question. So if this come in question 1, all 252 of you all would be ready. So we had 50 cm³ of, alright, you know this last question here of NOH, I'm just making it short. Temperature was 24 degrees Celsius And the concentration was, lots of information will be given in this question. 2 moles, but they will walk you through it if it's in question 1. 2 moles per dm cube. What is the temperature? Right. Ooh, this temperature question will take a little while, boy. There's a little trick in it. There's a little thing about it now. So you add in this. This is added. Moles per dm cube. This is added to the next 50 cm cube. But sometimes this have water involved too. I don't know if this guys keep thinking. 50 cm cube of sulfuric acid I went through a past paper already, so do polymers, I do polymers. You all just search me for organic chemistry if you didn't see it yet. Don't forget to press like on the video, don't forget to subscribe if you haven't, and don't forget to follow me on Instagram if you haven't, for more updates and them kind of thing. I'm trying to write out this question here, but my brain only shutting up. 1 mole per dm cube. I'm going to put the temperature first. 30 degrees and 1 more. This question real hard, well lengthy, not hard, but I hope I could do it with what's going on with me right now. And when we mix them together, the max temperature reached was 43.2. Anybody could do this question? Let me see some Y's in the chat if you could do this question. Let me see some N's if you can do this question. So, some Y's, some people can do the question, and some people kinda, most people is N for this question. Most people is N for this question. Some is Y, they can do it for sure. So we need to determine the number of moles of water. Is added to that, and the temperature is that. So we're assuming everybody react and thing. Okay, we just had to assume that. Okay. Let's write the equation first. NaOH plus H2SO4 giving me, I don't care what it really, I don't really care what it gives. Alright, I need to care because I need to balance the equation. NaSO4 plus H2. And balancing the equation now. Everything looking good? No, this have a 2 here. Oh gosh, boy. I'm messing my bad day, boy. That 2 boy had to be there for, boy. So if I put 2 in front of this now, 2 O's. I put 2 here too. Right. So that is the answer there. Right. So I leave all the 2 here. There are 2 there now. Right. Putting some aqueous up in the dance. So they didn't give it the equation, yeah, they didn't figure out the equation. So you have a 2-to-1 ratio. Right? Keep that in mind. Work out how many moles of H2SO4 we had. We're going to work out that. So I put that here. Moles H2SO4. I look for my connector. 2 moles per dm cube and we have 50 cm cube. So I'm connected there. 1 dm cube has 2 moles, so 50 cm cube will have 2 divided by 1000 multiplied by 50 equal to how much? 0.1. Need to balance check the hydrogens and NOH's thing. Cohen does help with every subject or thing. Bam, boop, bam. Alright, so we looking here saying is 0.1. A little ahead of you all now because I kind of speeded. Then I will call the moles in. Oh my gosh, I need to go and sleep. You'll see what I do there. This is the moles in. This question bound to come. Yeah, I know a lot of teachers saying that this question would come. I just writing real nonsense, but what going on with me? I just need to sleep. Alright, so this moles of H2SO4. That's why I wanted to do this question no matter what. People in the morning, if you're watching this, good morning. 3 hours and 23 minutes. It should load back up pretty fast. So we're trying to work out the moles of H2SO4. So we use the relationship. What is the relationship we had? I think it was 1 mole in every dm cube. So we had 1 dm cube equal 1 mole. A lot of people saying this coming for sure. A lot of teachers saying this coming for sure. Chem teachers and things. It remains to be seen. And then the next 50 again. So 50 cm cube would be 1 over 1000. You notice I'm changing it to 1000 because it's cm cube. So this was what? 0.05 moles H2SO4. So it lines up good because it had a 1 to 2 relationship. So I'm just using here for sake. So if it was 0.01 to 0.05, no, 0.1. I hope I get 0.1. You all, if I'm making little mistakes, anything you know are going on with me, just functioning on 0 battery. Yeah, I got 0.1. I forget what we're doing completely. What are we doing? Oh, we need to get how much moles of water. So this is 1. This is. It had to be equal to the same amount. So it will be 0.1 mole of water. You see how I get this 0.1 mole of water? Cohen, take a break, boss man. I'm not taking a break. When I go in and sleep, I gone. 0. So this is equal to the 0.1 moles of water. So we compare. So if you have 2 moles of this, you have 2 moles of that. If you have 0.1 mole of this, so then you need to put in all of that information. I'm going to make sure I'm correct. Right, so we have 0.1 moles of water. So we just figured out we have 0.1 mole of water. So to work out the heat of neutralization, this is the tricky part here. Please pay attention to this part. You know we have 0.1 mole, right? We'll come back to that. Because this is what the is doing, but we'll need to find out for 1 mole. So we'll come back to that. But this is the tricky part here. If you remember, and this question will come break up into pieces if it comes. If you remember, this was 24 and this was 30. So you need to find an average temperature. And this is how you do this. This is how you do this. You'll say it's 100 cm cube now because you add the 2 of them. The average temperature would be 24. And this is from memory. 24 plus, what is 30? 30 was the next one divided by 2. 27 degrees Celsius. So this is your average temperature at the start. So I put T1, you could put at start. So now we know the temperature change. And now it doesn't matter if it's in Celsius or Kelvin because it's a change. Why is in the chat if anybody understanding what I'm doing so far? I hope some people understanding what I'm doing so far. When I'm sleepy, I doesn't explain that good. So the delta theta, or the temperature change, right? Because MC delta theta, temperature change. Good. Delta T, putting T for temperature, yes, would be equal to, what's the final temperature? 43.2. What kind of thing that measure? I know to get 0.2, boy. Take away what we get for the average, 27. I think I make a mistake in the average. It wasn't 24, y'all. It was 29.4 in this question. So that would change my average here. That is just a mistake in the number in here. 9.4. So the average is going to be 29.7. Sleepiness. Blame it on the sleepiness. So the average is 29.7. 13.5. No, the average is not 13.5. It's 29.7. I make a mistake here. And when I was writing the question, I need to go and sleep. 29.7. Let me just finish this question quickly. So when I take it away now, it will be 29.4 here instead. I will get 13.5. So I'm done. I'm done with the reason I'm finding delta T. You need to find that to do E equal MC delta T. M, we already have that. C, we already have that. Delta T, we just found that. So now I can find the energy. And this will be the energy based on 0.1. But we need to find the energy based on 1. So let's put in these values. M was 100 because we are assuming 1 cm cube is equal to 1 gram. C was 4.2. They gave us that in joules per. You need to make sure that unit match up. Joules per gram per Celsius. And the next one was 13.5. So this is going to be 5670 joules. I just read off that. Because we are trying to finish quickly. So I didn't work out this. I just read this off. Hopefully that's correct. And double check it. And now we can say 0.1 moles gives that 5670 joules. So therefore 1 mole I can multiply by 10. Yeah, because that's like 1/10. 1 mole will give 5670. I can multiply by 0.1. Or not, multiply by 10. Multiply by 10. Find for 1, divide by 0.1, multiply by 1, which is the same as multiplying by 10, which is going to be 5670 joules. Right? Oh my gosh, this was hard to stumble through all of this in my condition, but I gotta take a sleep day, fellas. Let me just recap everything that we do. We did all. I would say we maybe do 40% of the syllabus. Less. 30% of the syllabus just now. I have all of organic chemistry up. If you still want to take a look at that, if you look at it already, you can do that. And the rest is up to you. Inorganic chemistry is up to you, learning of all them qualitative analysis. 56.7 kilojoules. 1, 2, 3. Jeez, boy. But for about 5 hours, I made no mistakes, and now I'm making real mistakes. Kilojoules. My bad. Alright. Yes, sorry about that. at the easy section you teach. No, actually the moles is what everybody, I did a survey on Instagram. That is what make me teach this section. Right? Everybody was moles, redox, electrochemistry. That is what people wanted. I gave the people them what they want. Yes, so I correctly mistake the 56.7. So, okay. I wish you the best in your chem exam tomorrow. Check out your channel one day. Gabriel Moore, you'll have to message me on Instagram, right? Because right now, I'm using this here, I can't check out your channel. I'm using a program, so I can't even check out your channel. Yeah, you put delta H negative. But they already say that. I don't think it's that what they, I don't think that's asking me to say that. Let me check. Let me just check and make sure. Yeah. Thanks again, chat. They was asking me about that. So the heat of neutralization, because it's an exothermic reaction, I'll need to put a negative. So I'll need to finish off by saying negative 56.7. The heat of neutralization, right? Kilojoules. I used to make that mistake back in school. Good luck, everybody. Recap what you do. I hope you're taking notes all the way through. Sorry for making them 3-4 mistakes at the end. Then they kind of spoil the perfect run. But I think I explained a lot. Be sure to tell me how it went on my Instagram tomorrow. I'm going to keep you waiting too long. Hold it down. That's 2-3 hour session, 6 hours. That's worth a lot of. It's just worth a lot. It's priceless, right? So hopefully that help a lot of people sort out their revision and this part of the syllabus. I pray that something we do comes exactly. This is why I did do it on the ending day, so it's not like the paper could change by tomorrow. Everything going on around easy. Relax, calm yourself. Make sure you get this 6, 7, 8 hours of sleep for some people. Recap in the morning. Draw what diagrams you need to draw in the morning. I will be praying for you all again. I pray for the ADMATs and I went down and prayed for the ADMATs and it worked. It worked. The ADMATs things we do on the night before just come back. The only thing that was hard was question 5 with the stationary points, but everything else was straightforward. So I'm praying for you all in this chemistry that what we do, everything, you all just smile and remember my voice saying this over. I don't know if you want to go to sleep with the video running in the background or something. Whatever you want to do, people tell me they do that. Like just zorsing into your mind. Alright, everybody rolling, so I could just end the stream here because I could keep talking and talking. Hold it down, people, wherever you're from. Ting.